sharing results, understanding the results, how far they are from optimal, and collaboratively improve their solution. So the idea is good and sounds kind of simple. Implementation is always difficult. So we have been working on this topic for about 7 years, 6 years. And each time we're building next generation of framework. And I think the last framework, what we came up with, collective knowledge, is basically a simple plugin-based workflow framework. So with our background in other domains, we realized that, in computer engineering, we don't have common experimental framework. And there are reasons for that, because again, the software is changing and so on, hardware is changing. So what we do is that we provide, for each of this component within the system, we just basically provide their own wrappers, very lightweight Python wrappers. But they have common API, so we unify API for each of this component. And we'll go through the whole stack, from algorithms to your frameworks, which you can have, your compilers, and down to hardware. And this framework, again, I just want to thank our first sponsors 2 years ago. So it was European Framework, FP7 Framework, and Tetracom project and ARM, who initially funded this project 3 years ago. So what happened with this framework? Sorry for this small outline. Afterwards, we start sharing different plugins for this framework with the community, and basically all available models, such as AlexNet, GoogleNet, there are mobile nets and so on. We start sharing those plugins for them with the community, and we also unify the meta information, how you can plug it in to this framework. At the same time, we start sharing wrappers around all available AI frameworks out there, so Caffe, Caffe2, CNTK, MXNet. Then we take those workflows, and it becomes really a tiny Python code, which we start sharing as well in the repository, so everyone can take some kind of scenario workflow which does image classification, for example, or object detection, run it on their system. And the fun part now is that usually when you do research, you are very limited with 1 or 2 platforms where you can run your experiments. And now, since you have a common framework, you can actually crowdsource your experiments across hundreds of different machines and so on. And then you can start collecting results because you have those common APIs and so on within some public or private repository. Repository doesn't have to be public, so with companies, some parts of the repository are private. But with the community, of course, we work a lot, and everything is becoming open source, open at the synology.org repo. So you can go there and you can see some of the graphs which I will show you today. Now, I wanted to mention a few concepts behind CK because, as I said, it's now taking off. We have more and more users, so I hope it may be useful for you. And the starting time may be complex if you don't know anything about it, so I want to give you some ideas behind it. What we notice is doing collaborative research for many years with different groups, you know that everyone has their own scripts to do some specific common tasks, like downloading, I don't know, TensorFlow, installing it, preparing your ImageNet for training and so on, compiling and running some front end for image classification, or if you do tuning of your BLAS libraries and so on. And everyone has their own kind of scripts with actions. So what we did is that for each of this script, basically, we provide our own, what we call CK Python module. And for each of the common action, we provide kind of an API within this Python module, so kind of simple thing. And if you start looking at many repositories which our users are sharing at GitHub and so on, you will have always the same structure now. So the structure, the first level directory, which you will see, basically the name of your module. And then what we do is that we provide a holder for all your artifacts which are there. So ImageNet, we are not converting it, we're just preparing a second level directory with a name, and we provide some JSON file, specific meta information about it, and then we just copy original artifact, or we provide a way to download it from the system. But now the whole thing is kind of what is important here is one person wrote, for example, their own program module and found out a way how to compile and run a program, but then everyone else within the group can start reusing this module instead of writing your own scripts and so on. So this puts us on the same page. And then basically collective knowledge framework, it's really tiny framework, Python framework, which you install on Windows, Linux, macOS, and so on with pip. And then you basically have those functions which you pull your repository, and then you start calling with a CK front end all those functions and modules. And that's all. I'm skipping some other things about how we unify input and output, but it's basically we serialize everything into JSON. But sounds like a simple concept. Why do we need it? It allows us very actually complex things. For example, all our workflows when we train a model, when we run a model, run inference and so on different platforms, we now provided all those pipelines, and you can see those repositories here if you want. And basically the front end for end user is, say, CK run image classification. So now all the rest underneath is hidden from a user. But someone else has to still write those wrappers. And of course, we provided within 1 or 2 years with collaboration with all our partners, we provided lots of wrappers. What they do, they basically adapt to the environment. Another problem is we always, when we write our own scripts, we hardwire names of compilers, of tools, and so on. So when compiler or tool is changing, API changed, so you are doomed. We have a real example when obviously we have been using Cafe 1 for a while with our end users. And when we just prepared and released all the workflows, Cafe 2 was released and no one was expecting it. And for the project, it was a disaster. So it was like you could suicide because you have to change the whole project. With our wrappers, because it was abstracted, we just provided a package for Cafe 2 and we just provided detection of Cafe 2 and transferred all your converted underneath all the image, all the data sets and so on to Cafe 2. So you, again, you abstracted from this, you didn't even see it. So researcher was really continued doing research as if there was no change. And this is a really powerful thing. Now, even though I mentioned that I'm not speaking much about research, of course there is some research going on. And of course, for 20 years, everyone was doing auto-tuning. And with all, when you have all the topology of your models, you have many compiler transformations, you have at all levels, you have different parameters. So what we do here is that auto-tuning and modeling of a behavior comes kind of as a side effect, because all those wrappers, again, we can start exposing in this information flow just several keys which are really related kind of to physics. So you model your behavior, which is your keys. These are your keys for execution time, code size, compilation time, energy, and so on. These are they depend on your choices underneath, and you also expose gradually different choices within the system, your model topology, your parameters, your compiler flags, possibly transformations within your math libraries, you gradually expose them. Some features, like, and the system state, like GPU frequency, CPU frequency, and so on. And then we basically start modeling the coarse-grained behavior of your system and trying to optimize it. So when we have it, basically, since we can crowdsource those workflows across many users, we can start running experiments at different people, and we can slightly tweak our choices, and then we can continuously monitor the behavior. And then this means that we kind of crowdsource auto-tuning as well, and we'll continuously search for better solutions. And then since we also share them, we can always just keep the best solutions on this Pareto or whatever your frontier. And then basically collaboratively people start optimizing their solutions at the same time. And then of course all the other things like modeling behavior, which is very important when you design next generation of hardware, it's all come to place as well. And it's kind of as a side effect of this unification. Now, some real experiments which we're doing, they're public experiments. What we have so far, and this everyone can use it actually now, is we converted, we started from object classification, object detection. Actually, there is much more coming up in a few months. We use Cafe 2, and TensorFlow. We have multiple libraries. And we provided much more data sets. We converted everything to CK. What we started analyzing is we still look at the execution time, but we also start looking at model accuracy, model size, device cost, and also power consumption. These are all the things which actually, if you look at all the research papers here, I think it covers most of the research which is needed, or experiments which you need to run. And then what is happening is we also provided a fun application, Android application, where you can actually download it if you look at this QR code. And this application actually connects to CK repository, downloads you slightly differently optimized versions of your Cafe, TensorFlow, different models, and so on. It runs it on your device. It measures different characteristics and sends it back to us. And then again, we're in a live repository. We see all the updates, so from different users. So each day it's kind of updating. It's really fun to see. So up to now, we released this Android application about 5 months ago. And up to now, there was about 1,000 downloads. We got about 700 distinct platforms participating. So when you do your own research, you usually compare your results against 1 or 2 platforms. And it's already hard. So here for free, we get really numerous platforms. We have 200 distinct CPUs, 100 distinct GPUs, and so on. So power range for these experiments is still quite small, but also, of course, you can add all the other dimensions there, which we are doing actually with other companies when you look at more powerful GPUs for supercomputers or oppositely tiny IoT devices. And what is important now that we continue showing those frontiers, but then the frontiers obviously depend on your scenario. So for one customer, we still need, for example, to find the best execution time versus cost. Again, when you have a mass production, you care about this. But then if you want a better accuracy, what is interesting is that suddenly your frontiers changes, and it's kind of normal that if you want a better accuracy, of course, it's more expensive and a bit slower because you need a big model usually and so on. But this allows you to kind of convert all your research and kind of data science. And it's really enabled collaborative research now. Just 2 more slides, and I think I have 3 minutes. What I'm telling you here, it's still not really proper optimization. We're just playing with coarse-grained choices. But then we had a task, and we started looking at one of those platforms, Firefly, which is an interesting platform. It's some kind of not too cheap, not too expensive. It's working not too bad. And we thought about how can we optimize it further. And then we started looking at different autotuners. And as I mentioned, we can easily plug in all the different autotuners which are out there or even do our own autotuning. So here, an interesting example, we have been collaborating with Cedric Nugerten from TomTom, who created this nice OpenCL-based BLAST library. And it has many optimizations which you can play with and with many ranges. And basically, we plugged it into our framework. We plugged it into Caffe, so it wasn't optimized outside with some random data sets. It was really inside the real application. But then whenever you run your image classification, each time we're tuning this library. And what we'll show you, just the last slide, just to give you a hint of what you can do with this kind of approach, is the following. So here, what I show on the graph, so for 3 different models, we show frames per second, basically. And we ran Caffe, and we compare five different libraries. So underneath math libraries was libDNN, CLBLAST, VNCL, CLBLAST. When we say CLBLAST, it was auto-tuned. So DVDT actually comes from acceleration, if someone didn't notice that. And OpenBLAST. And then we ran it on GPU and CPU. And this is ARM-based architecture, both CPU and GPU. So and what is happening is OpenBLAST, if you also tune batch sizes and so on, CPU is working really well. And there is a famous thing that if nowadays you try to run models on your GPU, the performance is really bad. And if you have been at the BOF by Pete, so he was also mentioning this. So here with auto-tuning, we actually got really nearly to CPU performance on this platform. And it's 4, 6, 7x speedups. So in such case, we can actually start really using heterogeneous kind of processing. So we can start running at the same time parts of your models on CPU and on GPU, but you really need auto-tuning. And this auto-tuning, as I mentioned, again, it came as a side effect of our unification. So we're not really doing special yet another auto-tuning framework for that. And finally, we share results. Everyone can reproduce them and build upon them. Because again, you have the common framework. So that's how we work with the community. The last slide, just as a conclusion. We now have a growing community around this approach. I'm very glad and I'm very thankful to all these partners who are using collective knowledge framework. But it's only very, very beginning, and there is really a lot to be done. And we're building a new consortium. Hello? Yeah. We're building a new academic industrial consortium, so who would participate in those kind of open competitions and so on. There is lots of interest, and if any of you are interested to participate, just get in touch because it's ongoing work. We will collaborate with several conferences, and I think it's a really interesting approach. The same, we continue with the community. We continue sharing all those artifacts which you use for your research. We unify them, we provide JSON API, so you can basically start plugging in all those artifacts to your research workflows. And instead of spending months and months on preparing experimentation, you can really spend one minute to start your experiments and then do innovation. Finally, a couple of more things. We improve models, and we also find missing features because we crowdsource all this approach. We crowdsource modeling. And our last hope, where we're moving towards, is online learning. So we want to actually distribute learning across many different devices. We have all the technology for this. So partners are welcome for this. OK, thank you very much.
OK, thanks to the speaker. We have a few minutes for some questions. Please raise your hand. OK.
That's right. For now, we are image-centric mainly because of our customers. But we start looking at other workloads. I didn't mention this, but text processing, audio processing, and everything is on the list. But it's part of our work is really public and academic, and I'm having fun there, but we still need to survive, and we need to feed ourselves, so we do what customers want. And this is still image-based processing.
Sure. Okay, thank you.
Yep. Okay.
Yep.
Let me introduce David from University of Dublin, Trinity College, to talk about parallel multi-channel convolution using general matrix multiplication.
Okay. Could we have it on the screen, please? Big screen. Sorry? My name's David Gregg. I'm from Trinity College Dublin. This is joint work that I've done with my research group, particularly with Andrew Anderson, who's here. So I'm going to be talking about a few different things. I'm particularly talking about doing convolution as found in convolutional neural networks and other types of neural networks using general matrix multiplication. And that's a pretty well-known strategy. And by far the best-known strategy for doing this is a method known as im2call, although im2call strictly is the operation that's done before the matrix multiplication. And there's an issue with im2call, which is that it needs quite a lot of memory. And we have come up with some improved ways of doing convolution that don't need as much memory, but still allow us to use gem. And I'm also going to say just a few words about when you've got a bunch of different approaches, how to select the good one. So if we think about multi-channel convolution, we've got an input image. We convolve it with a whole lot of kernels. Both the input image and the kernels have a bunch of channels. And each of these kernels gives us a single channel output image, which are concatenated together to form a stack of, to form a new set of images which become the channels of the next layer. So im2call is kind of the classical gem-based convolution. If you read the early papers, they said, wow, we can get this really good speed up by converting our convolution operation from a loop nest into a matrix multiplication. And it's pretty widely used in deep learning frameworks. And it's based on a very old idea around creating a tuplets matrix. And it's a great method, except that it expands the input size by a factor of k squared, where k is the dimensions of your kernel. So if you're doing a 3 by 3 convolution, the size of the image, or the amount of temporary space you need is 3 squared times the original input. And that's quite a lot of space if you're working on an embedded device or a kind of memory-constrained device. Now, this issue isn't nearly as big a problem if you're doing a strided convolution. And if all our convolutions were strided, we wouldn't have to worry too much about this. But unfortunately, very, very few of our convolutions are strided. So this can, as you can imagine, be a big problem on embedded systems and also on any sort of system where you've caches and you're worried about memory traffic and the energy that's used by memory traffic. So how does IM2CALL work? Well, you start off with your usual kernels. You've got your image, and the image gets replaced by what we call a patch matrix, and each of these patches is the dimensions of the k by k kernel, and we have w times h of them. So we end up with a piece of memory that's significantly larger than the original input. And then out of this, we finally get the result matrix as before. So we've got this issue with IM2CALL is that it needs quite a lot of space, and if we're working on embedded systems, we don't really like things that take a lot of space. And so what we've been working on for some time is, could we find another algorithm that allows us to have all the goodness of GEM, all the speed, all the ease of building the algorithm, but we don't have to build a patch matrix that uses all this space. And we propose a family of GEM-based algorithms, and they're based on a different way of writing the convolution using GEM. And they don't need a patch matrix, and they don't need a whole lot of extra memory. So if any of you have ever worked on vectorizing compilers, you will probably have tried to, or if you've ever written vectorized code for a simple 2D convolution on an image with a single channel, you'll probably have figured out at some point that actually the way to do 2D convolution is not to try and load 3 elements into a vector and things like this for a 3 by 3 convolution. The real way to do it is you take one element of the kernel and you multiply it by all the elements of the image. And then you take one element of the kernel and the next element of the kernel multiplied by all the elements of the image. So what we end up with, we've got this kernel here in this example with 3 by 3 kernel, and we're convolving the image. And the way that you do this, if you're writing it in vector code very commonly, is that you'll take the image and you'll produce 9 copies of the image, each multiplied by one element of the kernel. And that vectorizes very nicely, and people who've written the vectorized code will probably be very familiar with that. The problem is, of course, you can't just add these things up together. You can't just add all the matrices on top of each other, because relative to each other, they're all in the wrong place. But what you can do is you can say, well, okay, so I've got this top left matrix, which is the result of scaling the image by the top left pixel of the kernel. And if I take that and I just shift it over a bit, then all the elements will be in the right place. And similarly for each of the 9 elements, except for the middle one, which doesn't have to move. And that's a common way to vectorize convolution, just plain old convolution. And we were thinking, well, perhaps we could do something similar with multi-channel convolution with multiple kernels. And essentially what we did was we took our algorithm for scaling matrices and adding them together, and we replaced the scaling a matrix by a scalar with scaling a matrix by a 1-by-1 kernel. So a 1-by-1 kernel, it sounds ridiculous to do 1-by-1 convolution, but of course in DNN convolution we have multiple channels, so a 1-by-1 convolution starts to make sense. So we replace the matrix scaling by 1-by-1 DNN convolution, and then we do k squared of those convolutions, and then we need to add them up in the right order. And if we add them up in the right order, we'll get the right answer. And a very nice thing is that 1-by-1 DNN convolution is simply GEM. It's exactly the general matrix multiplication call. So no extra patch matrices are needed. Now, a downside of this approach is that we need to do more GEM calls. So we have to do k-squared GEM calls is one downside, and the other thing is we have to add them up in the right order, and that gets a little bit tricky. But we avoid using a whole load of extra space. So 1-by-1 DNN convolution, we've got a kernel that's of size 1, and so it's a very, very much simpler operation than more general matrix multiplication, or sorry, more general convolution, and it can be implemented with a single matrix multiplication. So my postdoc, Aravind Vasudevan, came up with what we call Aravin's accumulating algorithm. And we apply this exact approach where we do the one-by-one convolutions, we do the k-squared of them. We produce the k-squared output things, except these have multiple channels. And then we add them up in the correct way. And a way that we do this to avoid using lots of extra memory is that we just produce one of these output matrices at a time. So we need a temporary buffer that's the size of the original image, but not, k-squared times the size of the original image. And so that's quite a nice saving. It's a factor of k-squared saving in extra space, which is very nice. Now, adding them up in the right way is a bit complicated because, of course, the things are in different places. The result matrices, the results of doing these one-by-one convolutions, the things appear in the wrong places relative to each other. So we need to do a little bit of, we need to do post-pass shifting, what we call shifting and adding, where we kind of shift the matrices in memory and before we do the addition. Now, of course, we don't actually shift any matrices in memory. What we do is we do pointer arithmetic. But that allows us to kind of virtually shift the things in memory. And then we need to remember not to add certain things on because actually these things fall outside the boundaries of the correct answer. So we were pretty happy with that algorithm. And we thought we were doing great work. And then one of us had an idea, and they said, well, hold on. The GEM library, for those of you who know the GEM library, it doesn't just do matrix multiplication, it also does accumulation. It allows you to add a matrix onto a matrix. You can get a result matrix and you add it onto another existing matrix. So why don't we do the accumulation like that? And it's potentially faster than doing a post-pass loop because we do it as part of the gem call, and so we don't need to take an extra pass over the memory. We don't need to pull a whole load of extra stuff into memory. It improves locality. There are all sorts of advantages. Actually getting the algorithm to work is a little bit complicated. And there's a couple of complications. The first one is that we shift the result matrices when accumulating, and the gem call doesn't really have an option to shift the result matrices when accumulating. So we need to be very careful about how we do the pointer arithmetic to tell it where to write the data. There's another issue, which is that in all these, at least two-dimensional convolution algorithms, there's all sorts of special treatment of the edge pixels in the result and edge pixels in the input. And we have to deal correctly with these boundary pixels. Now, the GEM algorithm hasn't heard of boundary pixels. It doesn't know anything about them. All it knows is that it's doing matrix multiplication. So just to give you a little bit of a feeling for how we solved some of the things around accumulating into the right places, if you can see the input kernels on the right, so we've got 3 by 3 kernels, each with C channels. And if you see each of the letters A, B, C, D, E, F, this is a picture of where we need to tell the GEM algorithm to start writing the matrix result. So we tell the GEM algorithm that the result matrix starts here for when we're computing the A matrix. It starts here for the B matrix, here for the C matrix, and so on. And for some of the ones, for the ones from the bottom row, we need to tell the GEM algorithm that to start writing before the start of the result matrix. And it took us quite a while, actually, to figure that out. We actually thought it was going to be the opposite way around. But if you do that, then everything gets written in the right place. And apart from a whole load of boundary pixels, which have completely wrong values, quite a lot of the result is correct. So, kind of okay, kind of right is pretty good. So the next problem was, of course, that we were, how do we deal with these edge pixels to get the right answer? Because, of course, convolutions, they stop at the edge of the image. And we're building our one-by-one convolutions out of GEM. And we're kind of using GEM for a purpose it was never intended for. It's not intended for doing convolutions. We're telling it to, plonk down results in the middle of a matrix or before the start of a matrix that we're actually intent to write to. So all the boundaries we spill over into the next row of the result. And so we get kind of garbage, and we get lots of wrong values in the result matrix. So we had a couple of strategies that we tried to solve this. One of them was to try and fix up the values in a post-pass, and we found that was very, very inefficient. It had very, very poor locality. It was reasonably expensive, but it had terrible locality. so that strategy didn't work very well. And the other strategy we came up with was, well, maybe if we modify the input matrix, we can get the right answer. We can get the right answer to come out that we want to deal correctly with the boundaries. And so we carefully place zeros. And this is what I think of as a guillotine algorithm. Effectively, we take, this is our original image. So say we were doing the convolution for this 1-by-1 kernel. We need to take the original image and we chop off the rightmost and bottommost part of the original image, row of the original image. Now, we can't actually eliminate these things because GEM has certain requirements. It requires that the data is laid out in a certain order in memory. We can't chop the parts off it easily. But what we can do is we can fill these with zeros. And so as we do our computation, we take parts of the image, we fill them in with zeros, and then we recover them. And this will finally give us our correct answer. So looking at the kind of space complexity of the algorithms, aim to call requires one gem call, and it does k-squared CHWM, so that's the number of channels, the height of the image, the width of the image, and the number of kernels. And the extra space is quite large. And then for some of the other algorithms, the extra space becomes smaller. And actually, we need plus W plus H as well. It just struck me onto this, but it's not a big additional factor. Okay, so we did some experiments and we tried this out on an ARM Cortex A57 and an Intel Core i5 4570. The work that we're doing is specifically aimed at inference on small systems. So we used a mini batch size of 1. Now you might see we're going to show some comparisons with some other libraries, and the comparisons for them won't necessarily look fantastic. But I think what you should bear in mind is that a lot of those libraries are not really designed for a batch size equal to 1. So you shouldn't think really badly of them if they don't do all that well in some cases. Actually, in the initial case, we're not going to show them. So we've got multiple implementations of each method. So a problem that we have when we're doing this work is that we're comparing different convolution algorithms, and all of them have the same complexity, time complexity. And it's, small variations in how you implement these algorithms can make a big difference to an execution time. And when I say big, I mean, 10, 15, 20, 25% difference in execution time. And so it's very easy to compare 3 different algorithms and to get the opposite results just by doing slightly different tweaks. So what we did was we implemented a bunch of different variants. We had a summer intern who was very, very good and very enthusiastic. And he implemented a bunch of different variants. For him to call, we implemented 23 different variants. It seems ridiculous there'd be so many, but actually they fall out quite naturally. And we went with the fastest variant in each category. So in this one, we took a row major layout. Rather than copying all the data from the original image, we copy some of the data from the patch matrix as we build it, and that improves the locality. And then for Aragvin's accumulating algorithm, we did a row major strategy, and then for the gem accumulating algorithm, we did row major, and we called gem with A not transposed and B transposed. So what sort of results did we get from this? So here are some results in the Core i5. What we see is that, in general, Aragvin's algorithm doesn't do brilliantly. Im2call is a very good algorithm. It does well across a wide variety of things. And gem accumulating is perhaps a little bit worse in a lot of cases, but there's not much in it. If we go to multi-core, we see sometimes gem accumulating does a bit better, sometimes it does a bit worse. If we look at the Cortex A57, again, we see gem accumulating doing a little bit worse, sometimes a little bit better. And if we look at the ARM multi-core, we tend to see gem accumulating doing well. And we think that this is because the kind of cache sizes and things like that on the ARM processor are relatively small compared to the Intel processor. And so we start to see a bigger win from using less memory, particularly on the Cortex A57. And if we look at the extra memory required, we see, kind of orders of magnitude in differences in the amount of memory that's needed. So very, very large differences. We probably need to add a small additional factor into these. Now that I think of it, we didn't take it into account. But we see very, very large differences in the amount of memory used. Okay, so what would I say about that work? Well, DNN convolution can leverage optimized gem libraries, as everybody knows. Im2col is a great algorithm. It's a fast algorithm. It's really good, but it does need an awful lot of space. And our gem accumulating approach, it offers kind of similar performance, sometimes a little worse, sometimes a little better, but it really requires a tiny fraction of the additional space. So we're quite happy with that. So if we just have a very short moment, I might just talk about one or two other things. So we've got a paper on this on arXiv, and we're releasing our code shortly, if anybody's interested. In the process of doing this, we implemented a bunch of different convolution algorithms. And what we found was that there's kind of different major classes of convolution algorithms. And we thought, well, how do you choose which one to use? So we've got a simple loop nest, which tends to be good for memory size, but it's really hard to write it to be efficient. We've got the Im2col, which is good and it's good all-rounder algorithm, great for stride, terrible for memory size. We've our accumulating algorithm, great for memory size, not so great for strided. There's a MEC algorithm, memory efficient convolution, very interesting algorithm. The results in the paper on MEC show that it absolutely, it defeats every other algorithm in sight. No other algorithm can compete with it. We weren't able to reproduce that result in our experiments, and we found that actually in our implementation, the execution time is very poor, and it used a lot of memory, but maybe we're missing something. And then there's FFT convolution and Vinograd convolution. So there's many of these algorithms that have been proposed and are used. And we have a library of about 70 different convolutions, different variants of the algorithms. And we had this question, if we've got a whole bunch of implementations, how do we pick which is a good one to use? And in particular, we don't use the same memory formats, the same data sizes, the same memory layouts for different algorithms. We tend to pick ones that work well for that algorithm. So, well, if you want to get different implementations to work together, even if they're working in different formats, we have a legalization pass, and we can insert format conversions and things like this to fix those problems. But of course, those format conversions take time, and sometimes we need a chain of conversions. Maybe there isn't a direct conversion between these two different types. So we were wondering, given that we've got some algorithms are good for some things and not for others, what can we do about this? Is there some way we can select between them? And what we do is we profile each of the individual layers individually, but we find the right combination of different algorithms analytically. And we use a classical problem that's used in compilers, partition Boolean quadratic programming, and it's a classical optimization problem. It's used for, it can be used for register allocation, for instruction selection, for address mode selection, things like this. And what it allows you to do is it allows you to attach a cost to the different choices for different algorithms for each layer of a neural network, but it also allows you to attach a cost to the combinations. So we've got 3 choices here, 4 choices here, and these are the 12 choices of combinations. And so, for example, in this case, there's no transformation that'll bring you from one layout to the other. And what we saw from this is, here are just some very quick results. We only have them on Intel at the moment. Actually, Andrew has ARM results downstairs. But what we see is that if we look at different things, we see a simple direct algorithm. That doesn't really work terribly well. We've got Im2 and Kern2, which is our gem accumulating approaches, work reasonably well. The Kern2 works sorry. Then we've got Vinograd and FFT. But what we see is that if we take the combination of these two, chosen with the PBQP algorithm, we can select the really best implementation for each layer and get very nice speedups. And we see similar things using multiple cores. And we get very, very nice speedups. So what would you say? Key takeaways in this. There are lots of ways to do convolution. There's no one best way to do it. Some algorithms are only good in special cases, but you can get significant speedups from choosing the right one. In general, compilers are great. People should use compilers more. All these optimizations that we've developed for various purposes can be applied to all sorts of things, including neural networks. Okay, so thank you.
Okay, thanks to the speaker. We have just one question. Please raise your hand. No, okay, I have a question.
Oh, someone talking? No, all right. So you've done a nice analysis on the which one to pick for best performance and maybe data size as well. But did you think about the power consumption? Because sometimes the matrix is not big enough and you have all the memory. So if the memory bandwidth or the memory movement energy is lower than whatever you would use for like starting up the SIMD processor or something, then maybe it's actually better if you just run with the normal code.
Yes, I think you're absolutely right. And it's something that we should do, but it's not something that we have done. So yes, I think it's a good idea. Thank you.
Okay, thank you very much.
Okay, thank you.
Yep.
Good afternoon, everyone. I'm Do. I'm a first-year PhD student in the computer laboratory of University of Cambridge. And today I'm going to be presenting to you about this work, which I've done with one of the master students in our research group. And it's titled Multimodal Biomedical Image Segmentation by Neural Network Fusion. So first, let me start. Ooh, doesn't work. Okay. So first, let me start by introducing to you what is actually multimodal biomedical image. So in modern medical diagnosis, actually, the doctors and the radiologists, you actually use more than one type of medical imaging techniques to help you diagnose and treat the diseases. So for example, you can have the computed tomography, and we can have the magnetic resonance imaging, and we can also have what's called the positron emission tomography. So all the three different image modalities are shown below in the order. And so for many diseases, for example, for cancer and for brain tumor, actually, what the radiologists found is that if we use more than one image modality, it actually helps us to improve the diagnosis and the treatment. So, so for multimodal image segmentation, so for the images that can be closely registered, that means you can put the image aligned and for example, like the head image, because head is relatively a rigid body, so you can register the image of head in a very relatively easy way by just a rigid transformation. So you can register them in a close position, and you can stack them together so that you make them into an image, and each modality corresponds to one channel in the image. But it is actually very difficult to do so for many other parts of the human body area, because there's a lot of soft tissues in many parts of human body, for example, in the abdominal area. So the soft tissues deform very easily if you, between scans to scans, and it's actually, there's not a working co-registration methods to register all the soft tissues in the abdominal area. As you can see from the diagram on the right, so the soft tissues, they are all in different places. They cannot be registered in a simple way. But is this the end of the day? No. We can still have some way to actually take advantage of the multimodality data, even though they cannot be co-registered. So first, before that, let me first give you some idea about the architecture, which is a convolutional neural network architecture that we have been exploiting. So I think most of you are very familiar with the CNN already. So basically, in a CNN, we know that for the lower level, the layers will extract the lower level of image information, such as the edges and the blobs in the image. And gradually to the upper layers to extract more higher level features. For example, maybe in the second layer, for the car, it will extract some part of the car features, such as the wheels, the car windows. And then in the more higher layers, it will extract a more higher level concept, for example, the concept of the whole car. So what we are trying to exploit is that, so let's say we have different image modality, but we are looking at the same organ, for example, your liver or a tumor. So the higher level feature representation of that tumor should be relatively independent from the image modality that you are using. So if you view let's say a tumor in CT or MR image, it shouldn't affect that you actually still see that this is a tumor. So let me first introduce you maybe to one of the data sets we are using. So for this project, we are targeting one of the diseases called abdominal aortic aneurysm. So aneurysm is a disease that causes your aorta. So aorta is the main artery of human body, and it causes part of your aorta to have a balloon-like bulge. And this bulge is actually very deadly because once it ruptures, it will cause 40% of the death rate. And so in our data set, we have a CT and MR abdominal scans of 21 anonymous patients. And so below is an illustration of what is actually a segmentation task. So we have the image patches extracted in the axial plane, that means the horizontal plane. And so the task is actually to segment the image into different classes. So on the above, you can see this is a CT image. So we want to segment them into 5 different classes. And in the below is the MR image, which will be segmented into 4 different classes. So the CT image, so these 2 different image modalities has their advantages, disadvantages. So for CT image is able to show the blood and the calcium deposit much more clearer than the MR image. But MR image is able to show the boundaries between soft tissues much more clearer than CT image. So each has this advantage and disadvantage. So that's why we want to combine them together. And so for the neural network for segmentation, it's actually, we are using a very popular architecture, which is an encoder-decoder architecture. So the encoder, so this architecture has 2 parts. The first part is the encoder, which encodes the a raw image into a higher level feature representation. And we also have a decoder part, which decodes the higher level feature representation into what we call a segmentation map, which is the map you see on the right. And we also added 6 skip connections, which pass the lower layers in the encoder to lower layers in decoder, which has been shown to improve spatial accuracy in segmentation. And so a naive way to train, so we have the image data set has the CT modality and MR modality. So a naive way to use this data set is we train one model to segment the CT image. Image is taken from the same patient that we're looking at the same part of the body and it has the same disease. So we think that maybe we can use some way to actually exploit this shared information between different modality. So what we did is we have fused the middle layers of this encoder-decoder architecture so that this middle layer should correspond to what we think of as higher level concept of aorta. So all the information so we have the 2 different lower level layers for different image modality, but they share a higher level middle layers. So while training this architecture, what we do is we train the CT and MR pathway alternatively in each training iteration. So for example, when training the CT pathway, which you can see is red part, you will let the weights or parameters for the MR pathway to be fixed. and then train the CT pathway. And alternatively, in the next iteration, we will train the MR pathway, which is colored blue, while keeping the red part, which is the CT pathway, fixed. So, this model has several advantages. So the first advantage is that it actually has accelerated training. So this is a plot of the validation accuracy of the fusion CT and MR model and the separately trained CT and MR model. So I don't know if you can see clearly, but on the graph, the accuracy for fusion models actually rise much faster than the accuracy for the separately trained models. And we also observe that there's slightly improved segmentation accuracy. So by accuracy, what I mean is we measure the global pixel-wise accuracy. That means we see if every pixel is classified correctly or not. And so the accuracy for CT modality is close. So for fusion CT model, we have 99.1%. But for separately trained model, we have 98.8%. And the accuracy for the MR model, actually, for fusion MR model is actually much higher than that for separately trained. So the accuracy for fusion MR model is 98.5%, which is 1.2% higher than that of a separately trained MR model. And we also observe some other very interesting behavior of this fusion model. So what we call is a learned shared representation. So what we do is, if we go back a few slides, so what we do is we put a CT image there, and so in the share layer, there will be some activations, which we call is feature maps. We take out that feature map for CT image, and we then put an MR image to the MR pathway, and there will be also some activation in the share layer, and we take out that feature map as well. And we compute the feature representation distance between these two feature maps. So what we use is a cosine distance, which is shown in the formula below. And you basically can think of each feature map as a vector, and then you can compute this distance relatively easily. And what we observed is that, so for the fusion model, so on the left, it's a separately trained. So what we did is we take out the image sequence of the same patient. The one is CT sequence, and another is MR sequence. So we compute the feature distance between each image in the CT sequence and each image in the MR sequence. And we plot this distance in the 2D matrix way in the heat map. So basically, you can see that the colder the color is, that means there's smaller distance. The hotter the distance, the hotter the color is, that means it's more increased distance. So for fusion model, what have we observed is that for CT image, that showing the aneurysm. So you can imagine the CT image, it starts from here and it ends here. So they're numbered from 1 to 72. And the CT image starts showing aneurysm around the image 52. So you can see it's the bottom part of the region. So the CT image actually shows a smaller distance from MR image showing the same aneurysm condition. So you can see that this relatively blue area is basically where the aneurysm looked at from the CT perspective is actually similar to the image looked at from the MR perspective. And but for healthy aorta looked at using CT image modality, actually has a much larger distance from the MR image showing what we call an aortic aneurysm. And also for CT and MR image showing healthy aorta, they only have smaller distance when they are looking at the same part of the body. That means if I took a CT image at this position and only the MR image at this position will show a smaller distance. So which is a small blue square at the left side. But this behavior only exhibits in the fusion models. That means this model are trained in the fusion by fusing their middle layers, but it's not exhibited in the separately trained models, which is shown on the left. And we also observe some other interesting behavior is that, so we have a pre-aligned CT and MR image pair. That means it's the same area of the aorta, and it's pre-aligned. That means we try to register them together into the closed position. And if we then manually shift one of the image horizontally or vertically, it will actually increase the feature distance. And so for the fusion model, so on the right you can see it's a fusion model. In the middle is where there's no translation, so this very dark blue, that means the distance is small. But if you shift it, the distance will generally increase to hotter colors. But this is also, again, not exhibited in the separately trained model. And so the same effect also apply when we are manually rotating the pre-aligned images. So on above the blue line is for separately trained model, and below is the red line is for fusion trained model. That means if we manually rotate one of the image, the feature distance will increase. So we think that this behavior actually can be applied in future works to help us register the image in some way that can allow us to develop new methods to register maybe body areas that contain a lot of soft tissues. So in conclusion, we use the intermediate layer fusion to allow neural nets to make good use of the shared information between multimodality CT MR image dataset that cannot be closely co-registered. And so the fusion model train faster than the separately trained model and are more accurate and learn a shared representation of the aorta. And we also think that this could be potentially applied in the future to image registration researches. So this is the end of my presentation. Thank you.
Any question? Please raise your hand.
Omar from the University of Manchester. Thank you, very interesting presentation. Just going back to the accuracies, you compare the models separately, and then you fusion the models for the accuracy, when you show the accuracy of the...
You mean the this part?
Yes, exactly. The variance between single model and the fusion is very small.
Yeah, the difference is not so big, yeah.
Yes, so I'm not sure if you calculate any kind of confidence intervals between for the scores. Or
yeah, so if you want to compute confidence interval, you probably need a larger data set than that. So basically, what we did is we separate them randomly, them into test and training, and we try the best. We report the best scores that it obtained.
Okay, yeah, because it's very small, so I think with a confidence interval can give you a little bit more of the real variance between the two scores. So,
yeah, there could be some variance, but if we have a larger data set in future, we will actually see what's the variance of the accuracy. Yeah.
Thank you.
So we can, because we still have time, we can still have one question. One more, yeah. Please raise your hand. No? Okay, thanks to the speaker. Okay. Yeah.
Come catch me, babe. I'm falling. Come save me, baby. I'm calling.
Hi, I'm Jan-Paul Siebert from Glasgow University, and the title just trips off the tongue, but it's all about data efficiency in using DCNNs for image analysis. And I realize I'm between you and the coffee break, so I'll stay within time. Okay, so I run the Computer Vision for Autonomous Systems group at Computing Science at Glasgow University, and we're into robotic systems and vision systems, cheap vision systems for robotics. So what we'd really like to be able to do is have our vision systems operate on low power, low cost platforms, these things, the ubiquitously available a smartphone, or that sort of platform, perhaps using the components from it. The cameras, for example, in these are very high resolution and fabulously expensive. I think we priced at £12 for a high resolution camera module. So in robotics, we would love to be able to run our deep nets on these sorts of platforms and have cheap interfaces, as I say, low bandwidth interfaces. We would like to be able to use the smartphone in egocentric perception applications where you could just hang the phone around your neck and use it, for example, monitoring activity or in certain other activities where it's doing recording of what you're doing, what's going on around about you. But the real snag in using it is that at the moment, state-of-the-art nets can only process a patch of about 300 by 300 pixels in size. That patch has to be run over the image, or in fact you build an image pyramid, run the patch over the pyramid, and that takes time. So the forward path might only be a couple of milliseconds to run the model, but you've got to do it in many, many locations. So this really limits what you can do. So it would be nice if we didn't have to do that. And the hypothesis which I proposed here last year is that we can use a transformation that occurs between the retina and the primary visual cortex. So what our objective has been over the past year is to develop a proof of concept that we can take what's known as the retinocortical transform, the transformation between our retinas and the primary visual cortex, and that in effect squeezes down the data by up to about 2 orders of magnitude, potentially. So we haven't seen anybody else try this for a long time. There were attempts to do something similar back in the 80s. For those of short attention span, I'll just give you the results right now. So using a 4,000 node retina, we got about a factor of 7 decrease for our pilot study, about a factor of 7 decrease in the visual data going from the input to the retina to the output to the deep net. We have just implemented a 50,000 node high resolution retina, and that gives about a factor of 17 reduction. For our 4K node retina, we suffered about 5-ish% reduction with this very, very first pilot run. We haven't been able to realize the full reduction in terms of the net because we have to produce an image, a cortical image, rather than operate on the retina responses directly, but I'll explain what that's about. But we do experience a reduction in training as well, which we predicted. So let's go into what this is all about. So the approach, here we have a sort of sampling pattern of a retina. It's long been known that our vision is foveated. So if you stick your thumb out, what you see at arm's length in central field of view, about plus or minus 2.5 degrees of visual angle, is all that you see in full resolution. The rest gracefully fades out. In fact, exponential reduction in sampling density. Now, this is nature's way of controlling the amount of information going into the brain. And we have followed this strategy. It allows us to squeeze down the amount of visual information. So we have a pseudo-hexagonal tessellation there. This is a tessellation was developed originally by Clippingdale and Wilson at Warwick University a long time ago in the 80s. And the idea is very simple. If we can couple this tessellation to a deep net, then we can gain not only the reduction in data, but also if we apply the same sort of transformation that happens between the retina and the brain, we get a degree of rotation and scale invariance as well. And as is often cited in the biomimetic literature, if nature hadn't evolved this strategy in primates, our brains would weigh about 60 kilos, kind of like this guy here. So an overview of the pipeline that we implemented to test the concept. We have an input image, pardon the use of Lena, that was my MSc student. We have, for each of the sampling points, we have a Gaussian receptive field, essentially just a Gaussian weighted averaging of the input sample, so a Gaussian convolution that generates one response, high resolution in the center of the foveal region, going out to lower resolution at the periphery. This is what the cortical space looks like, and you notice it's split up the middle. Now, there's something that, unless you work in physiology, you're probably not aware of, is that your vision is split up the vertical meridian of each eye. So in each eye, the right half of the visual field goes to the left half of the brain, and the left half, sorry, of the retina, and the left half of the retina goes to the right half of the brain. And there's an overlap of about 1 or 2 degrees of visual angle. It turns out that this sort of falls out of the mathematics of the mapping, interestingly. Here we see it projected into an image. We wanted just to be able to use the standard machinery available for deep nets, so we haven't yet attempted to use the direct retinal sampled responses, which would be much more efficient. So we instead have rendered out an image, and then we apply a standard deep net to that image. This is our deep net classifier, which was developed for the pilot study. Now, vision isn't a passive activity. Vision requires active interaction with the environment. So unless something's very badly wrong, we don't tend to sit and stare into space. We direct our eyes because our eyes are being driven to complete some task. The only point of having vision is to be able to do something with it. So we have a gaze control system that directs the fovea, the high resolution part, to appropriate locations in the image. So overall rationale, the retina can substantially reduce the data space going into the net. The mapping affords a degree of scale and rotation invariance, and the fovea itself, the foveation, acts as an attentional spotlight. And one of the surprising things about this is that it has the potential to actually improve the performance of the system. This original retina we developed 10, 12 years ago, quite a time ago, and we use SIFT features at the back end of it. And one of the surprising things is that when we compared the performance of full resolution SIFT on the same image compared to the retina with the SIFT-like features we extracted out of the back of it, we actually got a performance improvement using the retina. And this might seem counterintuitive, but the reason is that supposing you're looking at somebody's face, you don't recognize the face from the skin pores, the highest resolution information. You might want to use that information to verify some aspect of the face, but you recognize the face from the gross structural architecture and features. So wiping away that extraneous information, setting the information in context, reduces the combinatorial explosion of feature relations, but also cuts down the amount of, just simply the amount of noise and extraneous clutter. So how do we do it? Retinal sampling, put down the sample points, the Gaussian receptive fields go down, and we create an image vector of the responses at each location. We can forward project them with smaller Gaussians to interpolate into an image in the cortical space. This is the 50,000 node retina. And this is the back projected image back into retinal space, having gone through the image vector to give a visualization of what the retina sees. And for the 50,000 node retina, you can see that the reduction in resolution from the fovea to the periphery isn't all that large. However, this image was 930 by 930 pixels, so that's about 800,000 pixels, where this is 50,000 samples. So already that's the potential in terms of data reduction. Now, the other slightly obvious thing, one of the questions we asked was, would this thing be able to learn? Because we have a very, very distorted output space. On the other hand, that's what's going on inside the back of your head as you look at this right now. So, as I said, inspired by the primate and human visual pathway, we process each half separately but combine it in a single image for this purpose, rather than having two cortical hemifields. The mapping preserves local information, and we have projected it using Gaussian, little Gaussian kernels to generate an image that we can operate on using standard DCNNs. So it's similar to the old log polar mapping. The log part actually takes place as part of the retinal sampling. It's a conformal angle-preserving mapping, so the Cauchy-Riemann condition holds. It gives partial scale and rotation invariance, if you can imagine that concept. And the cortical magnification, which is also seen in exactly the same in the brain, gives a very, very high resolution central field of view, progressively lower resolution peripheral field of view. So it's a bit like nature's zoom lens. We have about overall almost 180 degrees of visual field if you move your fingers out until you stop seeing them anymore. However, we have excellent central resolution set in the context of that entire field of view. The other interesting property is that for any size of contour, when we're fixating at the center of the contours, we have round about the same number of units of neural processing sampling the contour, so it does an automatic load balancing. So it puts the processing where it's required. Now, what I've shown here is when we project from the retina into the cortical space, we take each half of the visual field separately, and there's an alpha overlap parameter that sets in the polar mapping how much overlap we get between the two halves. And setting it from 0 to 30 pixels, as we see going round in a clockwise direction, that's 0, 5, 15, and 30 pixels of overlap, produces quite a markedly different mapping. We chose this mapping as a good compromise between the density of the samples being clustered together as against having too much overlap. The higher the density, then the less interpolation we need to do, therefore the more data reduction we get. But ideally, we wouldn't produce an image, a cortical image at all. We'd operate directly on these samples. We have done quite a lot of optimization to trade off between the sharpness of the cortical image versus aliasing. So for the 4,000 node input image, it was about 168 by 168 input pixels. As of only last week, we were up to the 930 by 930 input 50K node retina. So these results are hot off the press. So we've done the validation or the initial validation on the small retina, but not yet on the large retina. How to decide where the retina looks? Well, the requirements was to explore salient areas of the image. I was at a workshop in saliency last year, and we spent half of the workshop arguing about what saliency is. In this case, we take it to be the dictionary definition of that which is conspicuous or important. In other words, corners. And we also want the gaze control algorithm to prevent the system repeatedly just going back to where it had been looking. So, as anybody who's read Yarbus's book on eye movements, gaze control is highly dependent, highly task dependent. So whether you're looking at a room of faces like this or being asked to find somebody, your gaze motions will be very, very different. However, for a default gaze where you have an object, you want the thing to explore the object, find salient locations and to gather training images, this is the type of gaze control algorithm we have. We've got two maps. We have a saliency map and an inhibition of return map, which prevents return to the same location. So we have in each location of the input image where the retina visits, we stick down in our inhibition map a Gaussian about the size of the fovea. In our saliency map, we simply find, in this case, we use SIFT features as salient locations, and we put down the Gaussian envelope into the saliency map of where the SIFTs. Then we subtract the two maps such that the inhibition of return map is subtracted from the saliency map, and what's left is the peaks according to the salient positions that haven't been visited. So it's very, very simple, but sufficient for initial experiments to drive the retina around to look at interesting locations on some object that's going to be learned. So for the validation to show that the idea works on the 4K node retina, we wanted to, first of all, establish that the thing will learn. There was nothing to say that really with this type of DCNN and this very, very distorted image, it was going to learn anything. So, but having done that, we wanted to determine the data reduction improvement, whether the partial scale and rotation variance actually does improve the learning rates, and also determine the contribution between the foveated retinal sampling and the mapping that does the polar mapping to achieve scale and rotation, partial invariance. So for this little pilot experiment, we had only 4 classes of object, fairly household things like a brown bear, raccoon, keyboard, and basketball mesh, actually. About 2,500 training images and about 1,000 evaluation and test images for each class. And we have 4 sets. We have original data over the same field of view as the retina, the back-projected retinal information with no cortical mapping, and then the full retinocortical mapping itself. As I showed before, this is our DCNN, pretty standard. I think there's 3 or 4 levels of convolutional layers, and then a bottleneck and softmax at the end. And we're using linear rectification. Now, by comparing the different data sets, we can work out which the contribution from each part of the process. So as I said before, for the 4,000 node retina, we get about 7 times 7 visual data reduction. Our classification precision has gone down by about 5%, but that was a very early version of the retina, and I think with optimization we can do quite a lot better than that. We went down from about 16 epochs, from 25 to 16 epochs on the cortical image. So that was quite a substantial improvement. From the different classifications, so full resolution, it was 87%, 87.5% at full resolution. With just the retina, it goes down to 86 with the retinal sampling, then down to 82 with the full cortical transform. Therefore, the retinal subsampling seems to be reasonably well parameterized. We're not losing too much on that, but the cortical transform seems to be losing most. The hypothesis is that this is due to the interpolated projection, potentially, and that's what we'd like to get rid of in the next generation of this. We have only just had the 50K retina produced. It's produced using a similar annealing neural net, so it takes quite a bit of time. Originally, when we did this work, for 32,000 node retina took about a week of processing. Today, using a GTX 1080, it takes about 14 hours for the 50K node retina, but you only need to do it once. This, as I said, produced about a factor of 17 visual data reduction if you could just operate on those retinal responses themselves. And we're achieving about a factor of 6 almost compression in terms of the reduction of the size of the net. Our goal is to be able to use all of that to get right down to be able to process the visual data in a single gulp through the deep net at full speed. So as I say, recent work, 50K node retina is described. We have a real-time execution of the 50K node retina on NVIDIA GPU. That was Laurent Spallock, my MSc student. So this has been running on a mobile processor on a laptop, but on a 1080 Ti, it runs in about 13 milliseconds. And that's on the RGB channels. Python wrappers, works in most NVIDIA GPUs, and auto-detects things like atomic add, which can speed up the production of cortical images or back-projected images. We also have Ryan Wong, another MSc student, produced the thing running on an Apple iPhone. So we have that looking around, and the innovation there is that we're using the cortical space. We're applying the SIFT there to do the gaze control, which is more efficient because it's a much smaller space, of course. And finally, Tom Esperon, another MSc student, MSc IT student, who's actually a physiologist, has taken the main cell species for color ganglion cells in the retina and also the magnocellular pathway, the temporal change ganglion cells, and implemented these. And we've run the whole lot on the GPU, as I'll show. So here we see, or I would see if I have my glasses on. So this is the input retina. This is the thing just being applied to the RGB channels, and this is the output cortical image. And if you look at this, this is going on in your head. Yeah, kind of odd. So we see the effect of cortical magnification, and the basic idea is that scale changes manifest themselves as shifts along this axis. Rotations manifest themselves as variations up in the opposite axis. And that's real time. This is on the iPhone. So that's the scene that the iPhone's stuck down. He's only implemented it in black and white. So the feature locations, potential interest locations, are being picked up with a gaze control algorithm, a slightly different gaze control algorithm on the cortical image, which is driving the cell phone to sort of sit there and look around. We did this partly as a sort of demonstration of concept, and partly it would be nice to be able to use it to do data collection. So because the iPhone's field of view, image size is very large, we'll let the retina rove about that while updating the image at the same time. Now, here's an example of the color processing that goes on in the retina, and also how it impacts data efficiency. It's striking that people like DeepMind, when they try to do hand-eye coordination in robotics using simulation, will simulate the robot picking something up and putting it in the bin, but they'll do that for all possible rotations, different scales, and different background, foreground color changes, which is fantastic to show that you can do it end-to-end from pixels without applying anything else, but it's absolutely nuts in terms of signal processing. So what the retina does, it has difference of Gaussians type cells for intensity, and for color, it has blue-green and red-green or blue-yellow whole opponent cells, differential center or surround cells in B for red, green, blue, yellow, and it has what's called double opponent cells, where you have the same opponency, a central red-green with a larger surround red-green in opposite direction. So that these things are, so A is for detecting difference in color, B is for detecting color contour, and essentially the process in D is for detecting color texture. So this is already, these color contrasts are being detected so that we don't need to, so that it gives the gamut of color contrasts without having to go and learn them all. And you see a hint of these. So this is intensity, it's a sort of standard difference of Gaussian type map. And here we see the positive and negative responses for the blue, green, red, and yellow-blue cells. As a result, you can start to see the property of doing it that way is that the contrast between the two starts to produce a segmentation. The other part of the data efficiency is that the brain doesn't represent negative numbers directly. It has dual channels, so that the outputs of these cells, the positive output is in one channel, the negative output is made positive and down a different channel. And that automatically, by definition, gives the first stages of visual segmentation. So here we have the whole lot in one mega display. So what we see up here is the back projected response, the cortical response for color, the back projected response for intensity, and the cortical image. And this is for change, and these are temporal cells, so these are for the intensity images. It's looking at the differences in rate of change and having a positive and negative channel separated out. Now you switched it back just to the basic cells, and we see here the differential, the dog cells for intensity, and the color channels up above. So the next step is now to harness, and he's now messing about with, there's a perception threshold as to when these things kick in. He's now, so the next challenge is harnessing all of these within architectures. So, work in progress. We would like to validate the 50K node retina to find out what level of performance we can actually get out of that on a big data set in terms of improvement in training and data reduction. We're also very interested in being able to use things like TensorFlow and different input layer architectures, perhaps using lambda layers, to be able to specify each of the individual retinal positions. And I'm happy to talk to anybody who can tell me how to do this, along with the immediate neighbors, so that we don't need to build this cortical image. We can go directly to the retinal responses and get the full reduction. And then validate the entire, the color receptor fields along with this reduced space. We built the thing on an iPhone because that's what the student had. We intend to build it on an Android phone, which is a bit easier to distribute in terms of applications. So the projects we've got starting on the 1st of October is we have an Innovate project with a shadow robot company with a gripper. So we're building in-hand cameras as well as on-wrist cameras. And the retina would seem to fit quite nicely for grasping and hand-eye serving applications. We're working with Lars Mukli at the Neuroscience Institute at Glasgow University, investigating two things: how to structure the networks behind the retina in a similar way to how they're organized in the brain, and also looking at how higher order processes feed back into visual area 1 or our simulated visual area 1 to do higher order control. What you look at and what you perceive of what you look at only is considering about 10% of the visual information, or the information coming in from your eyes constitutes about 10% of the activity in visual area 1. So it's interesting to see how we can couple in potentially higher order processes to control with feedback loops the overall operation of the visual system. So what do we use this for? Well, this is our robot. It's a big Yaskawa Motoman robot, which was used for clothing manipulation. And we have you can see up in the top, stereo pair of cameras, and this is the machine calibrating itself. So we have a binocular vision system which we maintain versions and have gaze control processes on. So we would like to apply the retina in this context, and the nice thing is that applying the retina means for every process where you would be running the deep net over a little patch and scanning it over the entire image, that can be an entire field of view that's going through the net. So it's massively faster or massively lower power depending on how you apply it. This is the new shadow gripper, and we're mounting a camera in there, and that's where we intend to drive it using the retina. So, in conclusion, we've demonstrated that the retina DCNN combination will actually learn. So that was an unknown. It does reduce the size of input to the network. So removing the need to do patch scanning. So one gulp, the image goes in and through the net. It reduces the number of training epochs and produces comparable results. I think we can actually get better results using the retina. So our challenges and potential to use, to be able to process whole images on CNNs using what's there already, using cell phones right now. The challenge is to produce a custom layer to use the retina directly. As I say, if anybody has ideas on that, please talk to me. I'm interested in mimicking, as Steve Ferber mentioned yesterday, building architectures that fully exploit what's known about the brain. For example, the Gabor-like cells in V1, the pinwheel structure there. And exploit other biomimetic visual processing techniques. So one idea is to use a neuromorphic camera, and we might perhaps, so that each pixel only outputs when something changes, and instead of doing a warping transform, because these cameras are usually quite small arrays, we can take a lens that distorts applies a foveated view and down onto the array, and then it gives us a very efficient system since the bit of glass is doing some of the computing for us. And finally, the ongoing thing is how to integrate this system efficiently into hand-eye systems in robotics, for example, because one of the key bottlenecks in robotics is continuous perception, getting away from the old look, think, act paradigm in robotics. So, thank you.
Now it's question time again. Please raise your hand.
Nobody going to tell me how to fix my network?
Or,
I have just one small question.
Yeah.
And it seems that the idea of CNNs is that it seems like the idea of CNNs is that you can use the same filter to detect the same thing in different parts of the image, and that's the big strength of it. And when we introduce the foveated view, that kind of disappears to an extent, or
no.
Or I suppose the question is, why does that not disappear? Is it because there's some kind of affine transforms being done? Or
well, okay, my argument is, why should it? It's a conformal mapping. It's local angle preserving, so why should it disappear? The whole point of the mapping is that something in one field of view, small, will be similar in something in another part of the view, large. Okay, the sleight of hand or the constraint is that you have to be looking at what you want to recognize. If I'm talking to you, it's not just out of politeness that I'm looking at you. My vision system needs to look at you because that's the expected, the prior view that's expected. So if I'm looking at you, looking there, and I've got you out of the corner of my eye, the whole thing degrades quite rapidly. So in this style of processing, nature has evolved to use limited resources of the computing porridge up here to be able to process in a very, very sophisticated way. So it's boiling down the essential visual information, then doing a hell of a lot with it.
So you think that it'll be possible to detect things in the kind of periphery using the same filters as in the center, or do you think you need to use different filters on the periphery than the center?
The assumption is that it will be able to do that. Okay, the evidence I have that it should be able to do that is if you look at the V1 Gabor layer, the ice cube model of the orientation detectors, it's absolutely regular. So in the surface of the cortex, as you go around, you see the orientation directions change. But on the first layer of the cortex, it's a regular structure, and as you go down into the cortex, the size of the feature just enlarges, so that the architecture is remarkably uniform. Okay, the counter argument is, what the hell, it's all just made with neurons anyway, and there's no shortage of them. However, it would appear to be fair enough. The interesting thing is that the difference in learning is small, but the number of the training epochs have dropped substantially. And that's just allowing in-plane rotation and scale. And in terms of data efficiency, that's a massive data efficiency. So what we'd like to do is, on the input layer, stack up all of those different retinal ganglion cell responses so that the next layer, so that the first layer is the layer that copes with the sort of uniqueness of the structure, and it's regularized by the time it comes into the next layer. That's the hypothesis for the next piece of work. Okay.
Any more questions? And thanks for the speaker.
Come catch me, babe. I'm falling. Come save me, baby. I'm calling. Come save me, baby. I'm calling. Come catch me, baby. I'm falling. Come save me, baby. baby. I'm calling. Come catch me, babe. I'm falling. Come save me, baby. I'm calling. Come save me, baby. I'm calling. me, baby. I'm calling. Come catch me, babe. I'm falling. Come save me, baby.
Okay. Hello, everybody. Thank you very much for coming today. Yes, I definitely live. Perfect. Yes. So, so this is, despite the fact that it's in the main track, this is technically a GoingArm panel. And just for those of you who don't know what GoingArm is, it's obviously the best workshop ever. And it's basically a forum for users and application developers and tool vendors and system integrators and implementation folks to actually share experiences, kind of to basically experiences about ARM and about how they've dealt with us going into HPC and also learn from each other. And without further ado, we'll start by having our panelists introduce themselves and just quickly going from left to right.
Oh, no. Got to start with the other end.
Okay, fine. So you played with the buttons too much. So Scott Hara from Qualcomm, Kevin Pedretti from Sandia National Labs, Sumoto Shinji from Fujitsu, Mitsuhisa Sato from Riken, John Masters from Red Hat, and Eric van Hensbergen from ARM. Okay, I see what you're doing. So, if you'd like to introduce yourselves before we start with a kind of grilling and questioning.
Should I start?
Yeah, go ahead and start.
Okay. My name is Scott Hara. I'm from Qualcomm. I am responsible for Qualcomm's strategy for HPC.
Kevin Pedretti from Sandia National Laboratories in Albuquerque, New Mexico. I work on system software for large-scale HPC systems, from focusing on the operating system and also looking at virtualization technology, applying that to HPC.
My name is Shinichi Miyamoto from Fujitsu. Fujitsu has been working, developing for over 40 years for HPC system and software and hardware. So I'm in charge of HPC system 20 years. 20 years ago, there's a bit cluster, that's a pitch-based cluster. So in other cases, permanent pitch cluster. At the time, so maybe dedicated supercomputer mainly used. However, next 20 years, at now, it's pitch-based standard platform. So, next 20 years, ARM will be next chance to change the world. So, I hope currently working building up ARM ecosystem. Thank you very much.
So, my name is Sato from the Riken. So, I'm now in charge of the post-K development from the architecture side. So, as you know, so we have decided to use the ARM as an instruction set architecture for the post-K. So, and we are much focused on scalable vector extension.
Hi, I'm John Masters, Chief ARM Architect at Red Hat. And about 6.5 years ago, but who's counting, myself and a couple of others set up the Red Hat ARM team. And very recently, we've had releases of Red Hat Enterprise Linux Server for ARM, which is currently in development preview. And you could imagine that at some point in the future, that may change. So we're very interested in the opportunity for ARM in traditional enterprise and in emerging opportunities in public cloud and elsewhere. And look forward to being on the panel today.
And I'm Eric van Hensbergen. I'm with ARM Research. And I am also director for HPC at ARM, so I look after all the ARM HPC activities, including our involvements with Riken here in the EU and in the US.
Awesome. Okay, so the format is going to be, well, a little bit different. So I'm going to ask a question, and then we're going to go from right to left, and each of you is going to have one statement. Then we're going to follow up by questions from the audience. Anybody, even on the live stream, can tweet questions to us at GoingArm, and we'll read the questions over here, and you can respond to them. And of course, while answering questions, feel free to interrupt each other. All right, so first question. So what's your opinion on exascale computing while battling the end of Moore's Law? Nice, open-ended question, right?
Okay.
Scott, you're up.
So battling the end of Moore's Law. So let's make Moore's Law an observation that happened long ago, where he observed that we double our transistor density every 12 months, which eventually slid to 18 months and 24 months and now 40 to 60 months, right? So I actually don't think a lot is going to change. Early on, performance was driven by processor node. I don't think we've seen a strong correlation between performance and process since the 90s. I think our performance increases have happened through architecture advancements or changes. And I really strongly feel that that's the way it's going to happen for us to get from where we are today to exascale in 2020, 2021, 2024, or whenever it's going to happen. And I don't imagine our transistor budget will change very much. So it's, it puts a high burden on our architecture teams to put in place the features needed to accelerate in a performant and power efficient way the important codes that we have to run on these large scale machines. So my short answer is, I don't think things will change very much.
I agree.
Ditto.
Ditto. Done. Yeah, to a large degree, I think that's right. Leading up to exascale, I think we're kind of on a path where we're going to continue on. You know, at our current trajectory, I think we're probably going to get there. But looking longer term, it's clear that our exponential increases can't go on forever. I guess I would argue in the past we've had kind of a free lunch with Moore's Law, where performance has just kind of been increasing automatically for free. That's clearly tailed off recently and will continue to tail off. I think that's going to make both, that's going to make architecture more important. Architectural innovation, things like accelerators, those have started out being very special purpose, but over time they're becoming more and more general purpose. I also think there's going to be more emphasis placed on getting more efficiency out of the hardware, both application developers spending more time working harder to expose parallelism and get efficiency, and also in intelligent runtime systems and even operating systems to automatically exploit or try as best it can to map the application's parallelism to what's available in the hardware. So.
Awesome. Next.
I'm now Fujitsu, and then some vendors support exascale. It is a very, very concentrated power. So transistor consume power. So it's very important to how, which problem we are solved. That is predefined. So second step is how the transistor makes cache or some accumulator. It's very co-design phase. So we are working with Rick and application performance, also in the system software, almost a co-design. So the architecture is not so changed on the current architecture because the software maybe such kind of investment is so much continued so many years. So it is not so changes so fast. In that case, currently, so how focus what kind of problem we solve. That's my opinion.
One more rule before we move on. Ditto is not an answer.
Oh, okay.
Yeah, all synonyms?
Same.
Yeah.
We are inheriting a current architecture. Yes.
Okay, so first of all, the exascale is possible before the end of the Moore's law, so no problem. So, and Moore's law is not ended yet. So I think the problem is that that cost, the price of the power transistor is getting higher. Yes. So we have to solve the how to make the transistor more cheap. That is my answer.
So I agree with Scott. Actually, I don't agree with Scott. So I think the problem we've had is, I kind of agree with you. I think the problem we've had is that computing has been more or less cheap, especially from a software point of view. We've been able to get really lazy over the past couple of decades. If you talk to a lot of programmers these days, they're very, very abstracted from how machines actually work. And that's because we've been very fortunate that we can do that. But as we have seen over the past 5 to 10 years, Moore's law, whether it is fully over now or is imminently facing its demise, depending on who you ask and what interests they have, it's dying, and that does mean that we're going to have to care a lot more about the underlying hardware. And that's good, because I come from a software company, right? Now, traditionally, we sit in one box, and the hardware guys sit in a different box, and we never talk to each other. I'm a big fan of not doing that and actually working together. And I think we have an opportunity here to right some wrongs from the previous decades and actually come together and solve problems in an innovative way. And I'll give you one more point there. I think that if you look at what's happening with machine learning and you look at what's happening with workload acceleration, those are examples of ways in which we can say, to your point, Scott, around the dark silicon, the additional real estate we have on these chips. We're not just going to make them faster. We're not just going to make single-threaded performance that continues at the same rate of growth we've seen in the past, but we can use those transistors more wisely. And that gives me great hope that software folks out there can find this interesting again, and we can all right some wrongs from the past few decades.
So in kind of reflecting on it, right, during the petascale era, when DARPA was doing their HPCS program, there was a tail off there. It was frequency scaling. We started at a major system integrator that knew how to build these things and had a lot of confidence. The projection was for a 30 gigahertz machine to provide petascale. And yeah, it's only about 10x off the results. So, you know, these inflection points do have an impact, and I think in exascale, to the point someone made earlier, it really is in power. The exascale, original exascale projection lines and the power curves, especially the magic 50 gigaflops per watt number or 100 gigaflops per watt number, depending on whether you're talking about socket or system. You know, those were based on scaling curves where Moore's was healthy and at the same rate. And it's not, yeah, I also agree with Sato, it's not really the end, but there's this slowdown and there's this expense to which scaling no longer becomes practical, and some of the power and area advantages have reduced even more rapidly than the price increase as we keep going lower and lower. So it does create an interesting inflection point. I think it's closed the gap between the major incumbent in this area that used to have a 2-process node advantage over everybody else, and so they could just step on everybody, to now they're in a knife fight with everybody. And I think that's been another major inflection point, which is allowing us to re-diversify not just this ecosystem, but the server ecosystem. Whereas before it was a much more difficult game to play because they had such a tremendous advantage over everybody else. And in an area that was hard to catch up without significant investment. And so I think those things are going to lead to a greater level of diversity, and some of that will come through architectural innovation. Some of it will come through software, hardware, co-design, accelerators, and so forth. And I think that's what makes this an exciting time again, as opposed to just turning the crank and getting a bunch of stuff for free. So as a researcher, I think it's great.
Awesome. All right, so here comes the question and answer portion. Okay, so we have some people with microphones going around down there, so please wait for a mic to ask a question. Raise your hand. You got one right there up front.
So I think you said it has been free for a long time. I don't think it has. The cost of it was the growing pains that now we have to deal with it. Because it was a marketing stunt. It has always been. And it was something that was, people were like doubling it because it sells more CPUs. So I will do whatever I can. It doesn't matter the consequences as long as I can pay for them with money. And Intel had a lot of money. So now all of that has been encumbered into the design of the current systems. And this is what we have to deal with it. Right now, we don't have a choice anymore because the threshold has been hit. And the power law, the consumption, power consumption, and connectivity, all of these have power laws as well. And we have reached all of them at the same time. So the problem with exascale is not can we do it, is can we actually build a system that will be useful in an exascale type, right? Because we can build exascale systems, we just put lots of them together and, well, it's an exascale. But if it's actually useful or not, that will be the big deal. And that has to do with connectivity, has to do with power consumption, air conditioning, and everything else, right? Redundancy and all. So this is the cost that we now pay for all of the free lunch that they had in the past. I mean, that's fine.
Was there a question there as well? Or? Okay, awesome. Does anyone else?
We call that a Renato question.
Okay, in the back.
Free lunch is a touch word, yeah, so, sorry.
Just as a response to it, right, and I didn't include it in my original response, but what you're saying, it is one of the things I disagreed with some of the other panelists on. Yeah, yes, we have dark silicon, and maybe we can use that area, but one, it's not just power and area that we've hit the limits of, it's memory bandwidth as well. And yes, we may be able to find ways to use silicon to help that memory problem, but just putting more flops into it isn't going to be the way we solve that. The balance is a very important aspect of that, and something that comes out in co-design of real applications versus benchmarks. Okay.
And I wasn't trying to say it's not challenging. There are plenty of challenges, but if you look back multiple decades, right, at Sandia, our application developers have just been able to kind of turn the crank on an MPI everywhere model. And now, with the increasing on-node parallelism, there's a lot of effort being spent figuring out how to utilize that in a performance portable way. It's a big challenge. So, yeah, I agree with you on that. If you look at the current trends, though, I think there's a lot of things indicating we will be able to get to exascale. It will be challenging, but it will be doable. We will just be able to do it. We've got, things with on-package memory, giving us a big kind of one-time bump in memory bandwidth, and that's really important for a lot of memory bandwidth codes that we care about. And there have been significant energy efficiency improvements over the last several years, and some of the things on the horizon, that's going to continue. So I think that's probably going to be enough to get us there, but getting past there is going to be a really big challenge.
But that's the future thinking, right?
Yeah.
I mean, do we start thinking now in making systems that will scale much longer, or do we just continue the trend, still believe?
We need to think now, start thinking now. Yes,
Okay.
I agree, yeah.
I agree.
All right, next question in the back.
Okay. So I'm old enough to remember 20 years ago when Intel introduced a multi-processor chipset, and that made a huge difference back then. So recently they've come up with OmniPath, and you can now directly wire to CPUs, 26,000 CPUs together. That's 250,000 cores. So that's, and also it's shared memory as well if you want it to be. That looks like a heck of a change. Would anyone like to comment on what impact that you think that will have on the industry?
Well,
don't everybody jump at once.
So I'm not sure how big of a change that is. We have, systems that have 20,000 nodes or more today, interconnected with similar interconnects that also have, what's that? certainly from a trickle-down standpoint, that does change things.
I got a comment
go
on
ahead.
that. So again, I think Intel's a great company, caveat emptor, et cetera, right? I don't necessarily personally speak that with tremendous vigor, as you can tell, but what I would say is it's very easy to use it's commodity hardware defense always. You say, well, you know, we've got InfiniBand today in our traditional HPC systems. We can build all of these things. And if we have a big incumbent and they put this new interface on, suddenly it's commodity, everyone has it. Yes, but it's also a very closed, non-open standard that isn't going to lead to a broad, vibrant, open ecosystem of many companies participating and moving the world forward. It's good for them. It's a really good technology. Is it going to fundamentally change the industry? My personal opinion is no, it will not. And in fact, if anything, it will not help things. I think what we actually need to do is we need to take those concepts, we need to make them truly commodity, and the way we do it truly commodity is by having it be open and compatible and have open standards that everyone adheres to. And that is going to let us actually build machines that actually have all those marketing promises but deliver them in reality.
Yeah, just to pile onto that, right? There were lots of networks. There were lots of networks in the world prior to Ethernet, but it took an open standard to make the internet really possible. And
2 extra bytes.
Right, indeed. And I think that's it is a lock-in technology. Intel's made a game out of building this vertical stack that is all them: memory, storage, software. They are becoming a system integrator, an old-style system integrator, where they do everything. And the reason why my job's been so easy since I joined ARM of getting us into HPC is almost no one wants that. Everyone wants an open field with lots of competition and diversity because everyone needs something a little bit different and no one wants to pay 10 grand for a commodity processor, right? And the ARM ecosystem is the other end of the spectrum. We purposefully stay out of certain areas to give our partners chances to innovate in those areas. We do not acquire them and acquire their competition and then combine them and remove diversity. We are here to enable diversity because it's core to our business model. And I think that's a really important aspect of this. So open networking technologies, open standards. We're involved in the Gen Z initiative with HP, which is very similar in characteristics and goals to OmniPath, but it's an open standard, and it has AMD in it, and it has us in it, and IBM's been a part of it. And you have all of these traditional HP and IBM in the same room. That's fun, right? but at the same time, that's the best thing for that as an open standard. And the reason why those people are in the room is because Intel's trying to lock it all down. And everybody sees that. And the best thing in the world is when Intel tries to lock something down, it brings everybody else together and say, you know what, maybe we should work together and make a nice open standard that everyone can kind of play in this space. And we can still compete with each other, but we'll create this ecosystem, we'll create this diversity, and the customers will see the value in that. And I think the customers do see the value of that. No one wants to lock their data center into Intel into perpetuity other than Intel.
Yeah, I agree. I think in order to reach the efficiencies we have to, the vertical integration is necessary. However, done across open standards is the way we're going to do it, I think. And ARM is in a unique position where you can enable many companies to put their secret sauce of microarchitecture into it, and you can come up with interesting results. So now you can, through the open standards, through a diverse OEM or vendor ecosystem, you can choose best of breed for your particular problem. And I think that's the biggest difference. I think the co-design is important, which is really leading you to a vertical integration, but it can't be tightly coupled to one vendor. Mm-hmm. I think that's what's going to slow down innovation. But we do have to work as a community.
Yeah, I agree with you. Because when Fujitsu selected the ARM, that's the point. It's the same ISA, but different microarchitecture. So processor vendor can develop each focus, for example, application and solution. That's the point. So the real ecosystem, not only a single processor vendor, multiple processor vendors can compete and making a business and make within the business market. That is the most important thing, the ARM-based architecture.
But I had to say that more negative aspect. So so one of the important trend of the HPC is that the processor performance per chip is getting increased. So because of the accelerators or because of the many cores. So now is the 3 teraflops or something. So to support that's kind of the high performance, we need more bandwidth and more network bandwidth.
Yeah.
So that is not so beyond of the commodity. So at the moment of the PC cluster age, that we can share the HPC component to the very commodity one. But I'm very afraid that this kind of component technology is getting far from the commodity one.
All right, so we have.
Yeah, we've got 2 more questions.
We got 2 more questions in the audience, and we have our first ever Twitter question, so I want to ask this one first. All right, so Paul from Twitter asks, can you address the role of novel instruction sets versus ISA extensions versus coprocessors versus offload accelerators in exascale? It's a very large question. Thanks, Paul.
No.
All right, don't everybody jump at once?
Yeah, I mean, I think an important thing to consider is software in this case,
Really?
right? Yeah, it's amazing. An important thing to consider is software in this case, right? So, I mean, one of the benefits of ARM, and I think my colleague from Fujitsu was kind of getting at this earlier, is it is a single instruction set across many different potential implementations, which means that you've got a single software ecosystem. So if you allow arbitrary coprocessor instructions or arbitrary instruction set extension, then it starts to get messy. And ARM went through that several years back and decided, let's not do that again. And so that's an important thing to consider. I think having a standard ISA at the core is important. Now, accelerators is sort of an interesting one in that respect as well, though, because you can get into the same sort of mess with performance portability and code portability, right? I mean, NVIDIA's done a fantastic job in certain areas of the HPC space and also done a fantastic job of locking people in with CUDA. And there's really not a good viable alternative that people are using broadly. There's plenty of alternatives that people have been trying here and there, but it's essentially locks you into NVIDIA then. And that's dangerous too for the same reasons that lock-in and networking is dangerous. The expense that many of the leadership labs, and I'm sure Riken puts into developing and optimizing these codes, ends up dwarfing the cost of the system. And if you've got to change that every few years because you want to switch vendors, it's not viable. And then you get into that same danger of diversity again. So accelerators aren't necessarily a bad thing, but moving to a world where we've got a more standardized way of dealing with accelerators would be a good thing. And you can hide some of it behind libraries, and that's what the ML guys are doing for the most part at the moment. And there are HPC guys that do that as well. But it's a slippery slope. And so as we look at that world, we have to be very careful about how those accelerators integrate into our software ecosystem so that we don't get all of the bad aspects of ISA extensions just to get performance for a single generation.
I have a comment as well, surprisingly. So I think if we walk through them, right? So if you look at first, let's take ISAs and ISA extensions, right? So there's another company out there that rather famously used to have a choose your own pipeline model, where if you didn't like a particular instruction, you could add a new one. And that company's not really very successful anymore in comparison to ARM because they got bitten by the same thing that bites everybody. If you have to go and rebuild your software continually, right? Even if you're an enterprise guy like myself and you're in an HPC space because that's what your customers run, you could argue, well, a lot of those customers compile their own codes. They do, but they still want to run standard software as well. They want to run standard operating systems. They don't want to rebuild them. So that's out. Okay, so we're not going to do our own pipelines. Then let's look at instruction set extensions. If something is optional, it doesn't exist unless you're in a very special class of machine. Okay, we're in HPC. Maybe we say, all right, well, this extension is special. Well, that model can work. All right, let's take SVE as an example of that. Now, when I first heard of SVE, what I actually thought in my head was it's kind of like NVIDIA's warps, but done for compute, right? Because what NVIDIA did is they give you this model where you can scale based on the number of GPU resources you have. You can write your code one time, and when you run it, it's going to scale with the hardware resources that are available in that machine. And so SVE kind of gives you that benefit, but with mainstream compute. And it's designed right from the point of view that I can choose to implement a particular vector width, I can grow it over time, and there's some sanity there with how I deploy that. And I would also say for the case of workload acceleration, again, you can do it. You can target accelerators. I think you do have the issue of portability, of code portability. I think you have two standardization issues. I think you have the programming libraries and models you use, and you also have the ability to easily detect and use these. So from an OS point of view, I care about making these things boring to use. And I see a lot of machines out there today that have accelerators in them, but each one of them needs some special secret sauce magic driver, right, which we may or may not support. Customer has to go and hack the machine up to use it, and that creates friction. Even if you're in a special purpose leadership class machine that's just fit for one purpose and you're going to go and do that work, that's still work that you don't want to have to go and do every few years. So there's a lot of room for standardization. There's a lot of room for building generic libraries and interfaces.
Okay. So first of all, the supercomputers, which cost a lot of money, must be shared by the many users. So that means that so we have to support many application program. So accelerator is not so good for those kind of things. So and first of all, actually we offer of course the post-K computers that does not have the accelerators, not at all. So and first of all, our project is proposed a kind of accelerators, but application people is negative for that. So the reason, we gave up to have accelerators in our machine. So I think the SVE is a good design, and like SVE, some better design can improve the application performance overall in a reasonable way, I think.
To John's point, I totally agree. We want to be able to run standard software to some degree, and performance portability is the key challenge in all this, right? You want application developers to not have to deal with the nitty-gritty details of accelerators and reconfigurable computing and all this other stuff that people are talking about, right? But the fact of the matter is, on the really high-end systems, our users, and we run them, we want to optimize most of the system software stack up to the operating system with microarchitectural optimizations and so on. And we do recompile our codes frequently on a nightly basis, and that's just kind of how things are operated. So we're fine with recompiling our codes, I guess.
If I may, you actually hit upon one of the challenges and benefits we have with ARM, which is if you're used to a model where you have one very large incumbent architecture that people are targeting,
right?
You've got one microarchitecture at a time.
If there's one big platform, you've got one big system
right.
at a time. But
right.
even there's different implementations of ARM that
That's
have
the problem.
different
Exactly. Yes.
optimizations, and I imagine SVE is probably going to evolve over time, and we're going to, and compilers are going to evolve over time too to take advantage of those features. So we roll with that, and we kind of progress along as things advance.
Yeah, I think the key is Yeah, recompilation I don't know is a big problem. It's a big problem for Red Hat when they have to support. If you recompile, and you're like, it's broken, and they're like, well, which RPM did you use? They're like, oh no, we built it ourselves. They're like, okay, good luck.
Yeah, good luck to you.
And so I get that from
right,
the Red
but it's
Hat.
a different world.
But in general, I understand that that's the way the leadership class systems work. I think where the problem is and this goes in with accelerators, because there are advocates of accelerators that say, oh, yes, you can use an FPGA. I could take your C code and compile it to an FPGA and it just works.
Magic compiler.
Yeah. Magic compilers, yeah. I'm very skeptical of those folks. And some of them are in this room, and they'll excuse me for calling them out, but, or not. But that's, so I mean, that, and it'd be great if that was the case, but I've yet to see that be the case. And especially with reconfigurable logic, we've just turned a bunch of software problems into a hardware problem, which is also really interesting. And so that's a personal skepticism. So yeah, there is that danger, and it does get to that point where recompiling is fine, so I can take care of a newer version of the compiler with newer optimizations.
Yeah.
But when I have to dramatically refactor my code, or use intrinsics, a different set
That's
of intrinsics.
what we want to avoid, yeah.
Yeah, exactly. And as was pointed out, right, that was sort of one of the magic pieces of SVE with the vector length agnosticism. There was a conscious decision of, we've got to redesign the way that we approach SIMD and vectors. Let's not do it in a way where we have to reinvent the instruction set every 2 years.
Right.
Like the incumbents.
But as new instructions are added, that is a benefit, but you'll want to incorporate them.
No, of course, right.
So that is actually a question I had for ARM, I guess, is what is, I don't know, maybe.
No panelist questions to panelists.
No? It's not allowed?
I think we have time for one more audience question, and then let's move on to another topic question.
Well, let Kevin ask.
Well, I was just going to ask what kind of the path is to getting new instructions. This is probably a longer discussion than we want to have right now.
Yeah.
But clearly, the ISA evolves.
It involves a code offering.
Yeah, the path to new instructions with ARM is co-design, which you guys are involved with us with, and Riken and Fujitsu involved with us as well. Yeah. And I think, in general, we're a data-driven company. If folks come to us with problems that they think we can help them with the instruction set, we will work with them. Folks come with us with a very specific instruction, we may have problems.
But yeah,
from a patent perspective.
But you do it from ARM.
People that come to us with an AVX 512 op and say, "Can you just do this opcode?" We're like, "No, you can't because we don't want to be sued."
Yeah, but the model is you do it from ARM Inc. out, and then all the implementers of the ISA have to
just a brief correction, and then I'll let Jonathan
Okay.
redirect it out to the audience, and we can talk offline as well. It's not that we declare it from on high.
Well, yeah.
It's actually a standards body. Right, so Fujitsu is an architecture partner, and they're part of a group of architecture partners that we have to take the new instructions to that board for approval. And that's really the process. So it's just like any other standards body.
I think that's a good model, yeah.
Right?
Yeah.
Okay, Jonathan, I'm sorry.
All right, so the person that's been holding the mic for a very long time in the back.
You asked us to ask some questions, so I'd like to pose, rather than exascale being a point of interest. Now as a user, from once being a hardware guy, I see exascale as just a mini milestone. And my question is it not really that we see more benefit from sharing of the learnings from the programming model that we use to get to exascale than actually having a hardware exascale machine?
Kevin?
Yeah, that's a good point. This is the software ecosystem one.
So the question is, do the learnings in the programming model, the sharing of those, does our industry see a far wider benefit than somebody reaching a little milestone called exascale?
Historically, it's been more than just the programming model that's trickled down. But I mean, I think if you look at the history of HPC, there's a ton of technologies that were done for HPC initially, that then, at the time, people were like, who the heck, all right, would ever want to do that? And then 10 years later, everybody's doing it. And it's because, it gets pioneered in the Formula One version of computing And everyone finds ways, and then it trickles into commodity systems, and then everyone finds a way to leverage that in their own space. And that happens more often than people would like to admit. And it's one of the common things within a company when you're justifying, why is ARM doing HPC? Why did IBM do HPC? Why did Intel do HPC? Is a common justification. And it was actually kind of funny. Going in ARM, I made that argument and used data from my friends at the national labs to kind of show what the different trickle downs have been historically in that space. And they're like, yeah, but what about floating point? No one's ever going to use all that computation for anything. And then now here we are in the ML era where everyone's using obnoxious numbers of computations to do machine learning. And you know, a few years ago, there was no way you'd ever use all of the floating point power in any of these machines. But the ML guys are happily soaking it all up and putting it to some productive use. So I think it's a constant case study. This happens all the time. And not in every single aspect, potentially, but in maybe it's some of those aspects they just haven't trickled down into the right venue yet.
You know, Eric, you actually anticipated the next question perfectly.
Well, he anticipated the next question.
Okay. You lined it up, and so did he. All right, so what is the popularity of machine learning due to the design of future supercomputers? Oh. And so does the ML craze push HPC back towards LIMPAC-only machines? Or do we continue pursuing more balanced machines?
Yeah, I'll start and then I'll let the others, I'll be brief with it. I mean, I think the interesting thing, I don't think it pushes us back towards LIMPAC because LIMPAC's double precision and already machine learning's progressed beyond that. I think machine learning is evolving rapidly over time. And I think the techniques of today are largely techniques of opportunity because of the trickle down from in the HPC world and the graphics world have given folks reasonably cheap platforms to do things that way. I think folks are already looking at lots of different, more sophisticated ways to do ML than just throwing GEM at it, although GEM still is a primary component. I think, and there's a bunch of technologies like neuromorphic and all of these other things that are coming along as well. So from that perspective, I think at this moment in time, it's easy to see ML and HPC very lined up just because that's the hardware that's being used for both. But I think there will be some divergence at some point. And no doubt, eventually, some of those techniques will flow back into HPC, and some of the ways that we progress HPC will flow back into ML. But it's not necessarily a push us back to LIMPAC world. And memory is just as much of a problem for the ML world as it is in the HPC world, and that's the true bottleneck, not flops.
I think I agree with Eric. It's always going to be the case that for mainstream general purpose compute, which I would say HPC is a special case thereof, balanced designs are what you want to see. If you can't move the data from one place to another and then process it, then the machine's not useful. I think in the case of ML, I think we have machines today that are being shoehorned into uses for ML. And I think we're already seeing a lot of specialist hardware being used there, certainly for training models and for you've got the training and you've got the runtime, which is the two different pieces there. And you'll see specialist hardware for both. So I do think there'll be a divergence, and I do think that we won't go back to the bad old days, and we will continue to care about well-balanced machines.
So again, the general purpose supercomputer must be shared by the many users. So that means that not only the machine learning, another application must be supported. So, and I think again, the better design like SVE plus FP16 support or something can improve the performance of the machine learning. But machine learning demand is getting so large. So, you know, it's some cloud computing resources is specialized for the machine learning. In that case, I think a GPU or specialized hardware can pay for that.
I'm also same session with Sato-san. And LIMPAC is a very compute-intensive application. However, deep learning is In that case, cloud makes some huge data. In that case, some keep balance in the input and compute and output. This is very important. So in that in the manner, so in the keeping balance to input, output, and computing, that is important. So in my opinion, the general situation.
Yeah, there'll always be a place for balanced systems. There's workloads that will demand it. Even big data and machine learning workloads, right? Google's first tensor processor unit was memory bandwidth bound, and they rectified that in the second version. So, memory bandwidth is something that's also applicable to scientific computing workloads and will continue to be important for both worlds. And then in terms of software programming models, I guess there's trickle down from HPC, but there's also trickle up. The ML and big data world is, they have tons of different programming models and methods of accomplishing what they need to accomplish. And now, it's kind of upon the HPC community to figure out how to utilize that, leverage it, and incorporate it into our software stacks of our high-end machines. So things are flowing both ways, I guess, from my perspective.
Okay. So we're surely not going towards Linpack-focused machines. I don't believe that. I think even if you look at the workloads, deep learning, which have a focus on floating point, the floating point precisions are changing rapidly down to 8-bit and possibly 1-bit. It's all very researchy. I think what we're looking at is balanced machines, but the balance is going to be funky with acceleration across many places. I think a good portion of future HPC machines will be an evolution of what we do now, and there'll be pools of places where we have different types of acceleration, possibly ISO augmentation, like people said, which would be based on standards that we escalate through ARM, and possibly some fixed function units for places where we have a definite need, something that looks more appliance-like for particular workloads. The biggest difference is, I think, that if you look at the systems of today that may be doing interesting work, we'll look at the Fujitsu system that might be 6 years old, but still is #1 for HPCG and Graph 500. And the secret sauce to that is balanced memory to compute. I think that's the secret sauce going forward. There'll be certain pools that'll do different types of compute better, but generally speaking, we'll have these heterogeneous clusters with shared memory so we can access large pools of data between these more specialized and more balanced compute pools, I think.
Awesome. All right, so hold on, I'm on mute. Awesome. So I have one question from Twitter. So Ian Phillips writes in, is fine-grained HPC the future? In which case, is process in memory the ultimate architectural evolution?
What was the first part?
Fine-grained HPC.
So is fine-grained HPC the future?
Granularity is always an issue, right? Because as you get very fine grain, that ramps up the overhead. So I don't know if it's the future, but finding the balance in granularity is the key.
You're saying that processing memory, right?
Yes.
No.
Is anybody else?
So it's kind of the accelerator, right?
Yeah, it's an in-memory accelerator.
Same meaning. In-place computation is, appealing if we can figure out a way to leverage it in a usable way and inexpensive way, because this is new
with
stuff.
Performance portability across many clusters.
But, that sounds easy. Yeah, let's do this.
We should do that.
But I think that such kind of the processor can be attached to the general purpose processor like today's accelerators. So in that sense, it is possible, I think.
Yeah. All right.
We've got some questions from the audience.
Audience questions. Back in the center.
And one in front as well.
Okay, we got a microphone being passed over.
Yeah.
My question is, currently, user cannot access beyond what the instruction set offer from the vendors like ARM and Intel. If user can access beyond this instruction set, like for instance, micro operation we can access, then software people the best know about their application, then they can actually design, the best instruction. They can run the processor. So, I mean, the way we know the way Intel grows is, their instruction set is kind of monopolized, the market. Is there any reason or any technical challenge that that actually prohibit the software people cannot, or compiler guys cannot access beyond the instruction set? Clear about what I asked?
I think I'll take a stab at that. You may clarify and say it's not the direction you're going in, right? So I think you're asking, why do we have this model where software guys, I'm being nice to my brethren here, right? But why is it that we kind of don't really care until someone comes along with a hardware, with an ISA and tells us, hey, here's something we did.
Yeah.
And then we figure out how to use it. Is that what you're saying? Why don't we get involved in designing this stuff earlier? Is that what you're asking?
No, that's what trend we have in so far. So, but when the people actually design instruction, ISA, right? Instruction set, and there is a typically, the Intel, they using micro-operation, which actually implement the hardware. So, using micro-operation, they design instruction for the customer. So, but the application become diversified, and the probably most the Intel guy does not know about specific application people want to use an Intel chip. So similar maybe happened to the ARM. So why not they open up the application software guys actually access beyond the instruction. They design their own instruction for them.
Okay, I see where you're going with this. So I'll just touch on a kind of one quick comment on sort of microarchitecture. I think what you're alluding to is, say, on an x86 machine, you have these micro-ops, right? You have a micro-op cache, you have microcode, you decode instructions down into simpler instructions and so on. That's very, very both proprietary and very, very microarchitecture specific, and changes from one generation to the next, even across, if I just pick on Intel, even from, Skylake, Broadwell, different microarchitectures, it's going to vary wildly, and in fact, it's going to change even within a microarchitecture. If you have an errata, you have some kind of fix, you really can't expose that to programmers. They both won't know how to use it, and won't be able, they'll use it badly. You can't rely on any of the behavior there. And then if you look at where we're heading as an industry towards more of the risk, I realize that these other machines are actually risk internally at the back end, but if you look at where we are with ARM, a lot of the instructions that you're actually executing, they are the primitive instructions anyway. So essentially with ARM, we already have access to the very primitive instructions. And the thing we want to do is optimize our compilers to efficiently emit the right instructions and use them that way.
So previously, so we have proposed some extension of the ARM architectures, the SVE. So the ARM company is rejected. So main reason, they said, so maybe that Eric is the right person to answer. So that is because of the building the establishment ecosystem. So everyone must be shared the same instruction set architectures. That is very important to make an ecosystem. So that is coming from the bad experience of the previous architecture, right?
Right, and I think it's some combination of what John and Sato-san both said. It's like, first of all, everything I said before about why I don't think there should be arbitrary instruction set extensions holds, and that's what Sato-san was just saying. But even in the cases where we do have instructions that a particular microarchitecture might crack into micro-ops, there's a real danger if you try to target that directly, because, as John said, you'll get shifts from chip rev to chip rev that the vendors rely on their ability to hide that from you in the micro-op processing. And so your software management, maintenance, verification problems would just explode if all of that detail was exposed. But as John said, yeah, there's not being a risk architecture, natively a risk architecture, although some would argue that ARM's no longer risk, but anyways, it's unlikely that you'd really want, there's not that much opportunity in that reduction in granularity with the ARM instruction set. I've not seen it proven that there would be anything that you could really get out of that.
All right, so I think we had one more question in the back left back there, but in the interest of time, let's, from the panelists, let's limit it to 2 to 3 sentences response. All right.
So I'll make this a false dichotomy, which will make that even easier for y'all, maybe. So one thing that kind of keeps on is sort of heterogeneity and effectively more and more microarchitectural heterogeneity, things like processor memory, accelerators, what have you, all these different things effectively are different forms of heterogeneity. I'm curious about what your thoughts are on how to address the programmability of those type of architectures and to set up a false dichotomy between is this mostly a job for system software and tools, or is this mostly a job for just train up your programmers and just man-houred it out, kind of?
You want that, Kevin?
Yeah.
You can only choose one.
I'm supposed to, and 2 or 3 sentences, so.
Yeah.
I think coming up with intermediate layers that abstract away as much as possible the hardware heterogeneity is a attractive approach if we can succeed at that. At Sandia, we're working on this layer called COCOS that provides an interface, front-end interface where application developers define their data structures and kind of abstract coordinate space, define tasks, and then the COCOS layer can reorder data and perform tasking, scheduling onto GPUs or multi-core CPUs or other devices. That's kind of the approach we're trying to take and prove out. So.
Any other responses?
I think we overestimate the sophistication of the panelists here and in the audience. I mean, as a chip vendor, we want to make this acceleration and performance available to everybody. And it's just like a small portion of the HPC market. Many people don't even know where to get the optimized libraries or what -02 is. So, I mean, we have to make this simpler. We can't count on changing a Java programmer into a Fortran programmer or somebody who understands a more explicit language. I think the goal is to make it easier, make it boring. Yeah. So.
Well, let's be clear. Most people don't even know what an optimized library is. I mean, we lived through having 32-bit x86 machines for a long time, where you would push people and say, you know what, you can get an i686 version of your C library that's going to make it go faster if you run this one command, and you couldn't make them do that. So I think what you have to do is put it in the system software and tools and make it as invisible as you can.
Well,
absolutely.
Yeah.
Yeah.
How do you get the extra
Yes.
You're blowing away opportunity.
Well, because as we said, I'll shut up in a second, but as we said, these machines, even though they are specialist machines compared to, say, mass market commodity machines, they need to have general, they need to be generally applicable to a wide variety of programmers of different levels of sophistication. And a lot of those programmers, by the way, are writing code in languages like Fortran. They're not writing optimized assembly code. So it's been a while since I wrote Fortran, but the last time I did that, it didn't have the kind of architectural hinting that we would need to achieve this.
Yeah. And that's been the feedback we've had in interactions with people. One of the reasons why we didn't go down a heavy GPU path from a research direction within ARM was there were applications where 100% GPU would have been the right choice, but there was only about 30% of those applications, 30% of the set, of the wider set that we were looking at applied there, and we'd leave the other 70% on the floor. And when you're paying a couple $100 million for a machine, unless you're a specific industry like oil and gas and you know GPUs work for you and whatever, you don't want to waste that investment. You want to have it for the broadest set of possibilities. So it's not that you want to prevent people from being able to go in and wire things, but you don't want to have to require them from going in and doing that specialization. Because that's too heavy of a tax to pay. Kevin can quote the right numbers, but they've got hundreds of millions of lines of code within the DOE that equate to, I don't know, I think I've heard Tooks say numbers like billions of dollars of investment. Yeah. And by the way, some of the Fortran programmers that wrote that aren't alive anymore, and no one understands their algorithms and well enough to reproduce them. So it's they physically can't go back and rewire some of those codes. And you definitely don't want to have to do $1 billion software investment every couple of years, even though it would be great for the software engineering community. Lots of jobs, I suppose.
I think the heterogeneity, for the heterogeneity, people think that two things. One is the heterogeneity is between the nodes. So this node is faster and this node is slower. But heterogeneity for the accelerators, also is heterogeneity used for the accelerators. I think a programmer's point of view, the programming for the accelerators is going to be converged to like OpenCL and the data parallel programming. So, but still we have the problem performance portabilities. So each accelerators have the different performance and the different tuning point. Even we can use the same programming model. So that is the, I think, serious problem now.
All right, so no more responses. We have one more question from here. Change the subject slightly. So how do you envision the future of memory and storage separation? As in, do you envision continuing forward with a separate storage, as in block I/O, and a separate memory space? And if you envision these going together, how do you envision this playing out from the hardware, operating system, and runtime perspective?
I got an answer.
I don't know an answer.
No, that's a question.
I could take a stab at it if you want. Never underestimate how slowly this industry moves. I think when non-volatile memory first became a thing that people were interested in, the very first thing I heard from people is, oh, that kind of looks a bit like a block device. I think I'll put a file system on it. And you say, well, why do you want to do that? And oh God, why are you putting the same crafty file system you're running on your spinning disks on that, right? Because that's what they've always done. So we've already done that. We've already treated them like block devices and gone down that path. And we'll continue to do it because the industry is very, very slow moving and stodgy and very inclined to do what it's done before. And I would just add, though, that there are good reasons for this. If you look at where we're going with the transition to non-volatile memories, in particular, you go from a world where if you have a machine today that crashes, the state is ephemeral. I've got my persistent storage, I've got my runtime. Now if I have a machine that falls over and splats over RAM, it also might potentially splat over some non-volatile storage and blow away something I care about. So now you've got to do background scrubbing and all kinds of long-term data management and all these things, and that's going to take so much time to get right that, yes, they'll probably treat them separately for a long time to come.
Yeah, I mean, I think there's already cases where they're used in different ways. So, for example, the national labs in the US have burst buffers now, where the NVM is solving a key I/O bottleneck in a way that's different than sort of very traditional block storage. But to John's point, right, I think that's not going to completely converge and eliminate traditional file systems. I mean, most of the leadership class systems still have tape at some point. So when the tape goes away, we can start talking about the disks going away, I think. Yeah, exactly. Yeah, it's my IBM heritage. The tape speeds are very important.
It's food off a virtual punch card.
Yeah, no, indeed. That's awesome. So I think no matter what happens with NVM and when we get byte addressable and deal with all sorts of the nasty issues like John mentioned, as well as durability and all of these other things, regardless of all of that, there'll be a heavy tail on traditional storage methodologies as well. And yes, we'll find interesting ways to use these new technologies, but they also cause interesting problems. A lot of these HPC systems, they're not cloud per se, but they're very multi-tenant. And especially within the government, they're somewhat sensitive to the next guy that runs on the box being able to look in the memory and go, oh, look at that. That's an interesting simulation result. So, there's a lot of problems to solve before it becomes background noise in the overall system as usual. And it's nice I think there's a lot better ways to use it than just block storage, and I think those ways will come out and will be used, but at the same time, there'll be a heavy tail.
We've got some questions from the audience, right at the front.
And I also comment to the other questions.
Oh, okay,
Yeah,
that's fine
it
then.
was a Renato question.
Oh.
So any other audience questions? Raise your hand. Oh, we got one right there.
I would like to ask, how do you ask the near future of the high-performance computing? I mean the following. In the case of the real applications, you have serious performance problems, serious efficiency problems. Presently, the Taihu Light runs the real application with 0.3% efficiency. And it is not yet at the exascale limit. So what kind of applications are planned when you reach the exascale? And the other thing, how do you think, is there any upper limit in the supercomputer performance?
I mean, the basic answer to that is the balance stuff that we were talking about before. You can absolutely look across the leadership machines and see really low efficiency levels. Fujitsu actually has done the best. So good on you.
Right, but what the efficiency is still percentages, right?
Yeah,
like
yeah, of course.
I mean, this is a fact that most of
But exascale, the interesting thing with exascale is a modifier, so it's not that you have to hit, an exaflop, it's just that you have to do so many X better on that efficiency. And efficiency is actually the best thing to address. Yes. Just by rebalancing the systems to have better memory bandwidth, better latency properties and things like that, you can actually get a tremendous amount of that scaling than just throwing hardware at the problem, because throwing hardware at the problem throwing extra hardware at the problem is no longer the tractable answer. It really is now an efficiency game. And actually, Shekhar really expresses this really well. He kind of looks at the scaling and all of the curves tailing off, and he says, yeah, we're kind of screwed, but we're only running at 0.5% of efficiency, so why don't we just fix that instead of throwing more hardware at the problem? And we can really quickly get these multipliers that we're looking for. And I do think that that's the right answer. It's through co-design and balance that we get to exascale in these opportunities.
So if we talking to the performance of the supercomputer or the high-end system, there are two things. One is the capability computing, and another is the capacity computing. So for our experience, in the age of the K-computer design, so K-computer design is much focused on capability computing. So what kind of the computation, what kind of the science could be possible using the one program which is running on a K-computer. But in reality, that is the stupid things. So the application people is using the system in a medium size, running in many the jobs. So I think in exascale ages, the capacity type of the computation getting more important, I think.
Okay, and what is the sense of having a high precision weather forecast program, which from the today's data will tell in a year what was the weather?
Precision. Precision?
Precision? Well, you're saying because it takes so long to do a weather prediction model, the data isn't relevant by the time you get it. I think.
What's the purpose?
But that's not always the case, right? I mean, if you look at the weather models for some of the recent hurricanes, and sometimes they're wrong, admittedly, right? But they've actually been much better than they've used to be, right? And it's not a year later; they're able to do that relatively real time.
So of course, that's kind of the long trajectory type of the application is very important. So, for example, Anton is the specialized machine of the molecular dynamics is producing a very good result of the long trajectory application. But the another people is trying to do such kind of application, the application by dividing the trajectory and take statistics of that and predict the behavior of the many the phenomena. So that is the way to, another way to take a precision. So for example, in case of the weather prediction, so now is many people is using the technique of the data assimilation. So in the middle, the assimilate the data to correct the precision or something like that.
I think one of the things we're going to see is, as we're saying, throwing just more and more compute at this has limits, right? One of the things from a tractability point of view we haven't touched on, I think, is fault tolerance and RAS and these pieces as well. Because if you are in a emerging cloud space and you lose a few nodes, you don't really care as much as you do in a leadership class machine where you've got interdependencies between them at runtime. So I think what we can do in addition to increasing efficiency is also to address better fault containment and better, we traditionally call this RAS, but there's really a lot more to this going forward in terms of being able to more smartly use what we have.
All right, so I think that's all we have time for that one. So for another question, so from a hardware designer's perspective, how do you envision the programmability of extremely heterogeneous devices, and how does this programmability influence the devices that we actually build?
From a hard,
what is the devices?
So basically the question is, how do we break the loop between we write software for a particular set of hardware, we design hardware for that exact software, and basically we continue the exact parameters over and over and over. How do we, from a hardware designer's perspective, break out of this loop? One, enabling programmers to write programs like they actually want to write them, and then two, allowing hardware designers to actually exploit the hardware to the fullest.
So I think that at this moment that the accelerator device is programmed by the same type of the programming system. So it's a data pattern.
I don't know that. Go ahead. I was just going to say, I don't know if application developers know how they want to write code until they, see it. So, it's kind of interesting to look at how GPUs and general purpose GPUs have evolved over time. Like, before they existed, I think if you asked application developers if they wanted to program, in CUDA or some model like it, they'd say, no way, that's way too hard. But once the hardware is available and has all this potential to take care of, then there were, some number of users that were jumping up and down to try and figure out how to adapt their codes to that. And then it's kind of snowballed from there. So there's a certain level of disruption that is often needed to kind of progress the programming models forward.
So even of FPGA, many people is using the OpenCL as a basis, not directly to the VHDL.
I think the Apple model, just because we're on an Apple launch day and some of us are itching to go and watch a keynote later on, right? So See, you're all laughing. I know you are, right? Yeah. There's always, no. The good news is it starts an hour after we're finished, so you're all right, right? But there is that Apple model of if you ask people what they want, then they'll never get it, right? You just have to go and tell them what's good for them, right? So you could take that approach, and I think there's a certain sense with which it'd be nice if hardware companies did that. GPUs and FPGAs are interesting because they offer orders of magnitude. Yeah, but you've got to have a carrot, right? The carrot is, I'm going to give you a lot more performance, right? If you don't have that carrot, then what else can you do? Well, what else you can do is you can break the cycle that we live in. We live in a cycle where people use one incumbent architecture everywhere. It's on their laptop. It's what they're using all the time. And you can get programmers interested in talking with hardware people as well. Because today, we live in two different camps, right? We sit on this side, right? They sit over there. And what we need to do is not do that.
Yeah, I mean, from the hardware perspective, we have to deliver compelling reasons for people to try it. And I think also as a hardware implementer, we have to participate more closely in co-design. I think squeezing all the performance out, to partially answer your question, will be a co-design problem. And we've looked at things like this around DSLs and such things, which are difficult, if not so pointed that it's almost unusable, except for very, very small communities. So I think this is a big problem. I think we have to figure this out. I don't think I have a good answer.
Any more responses? All right. Let's move it back to the audience. Do we have any questions? All right, so we got one back left, and then we'll go here.
One sort of more general question I've got is that read shared data scales easily. Write shared data doesn't scale. You know, for me, I've always thought this was the sort of werewolf or vampire going forward. And in the end, everything might grind to a halt and we might not be able to push any further because we can't scale write shared data. Would anyone like to comment on that?
Write shared data. It's a bottleneck, serialization point.
Yeah.
No
you can fix that, right, Kevin?
No.
It depends what you mean. Are you talking about shared memory machines?
That's the first time I've seen this panel speechless.
No, you're right. That's another aspect of balance, right? So we've talked a lot about memory and processor balance, but balance on I/O is also important. Shared memory is not necessarily the way you get that. People claim it's a productive thing, but in most cases, when you hide things, when you hide too much from a user, you also let them shoot themselves in the foot. And so I think, you know, there's certain applications where shared memory is what you want, and don't get me wrong, and there's ways of doing it properly, but you know, you don't want exascale coherent access machine. You know, it'd be wonderful, but expensive in so many different ways. And so, but looking at, and this is actually an interesting point that you bring up though, because in early days, on a lot of stuff, all you see is socket performance or maybe single node performance. And if you look at why some of the efficiency numbers are where they're at, it's because they're basically taking the peak flops of a socket and then multiplying it by the number of sockets in a 200,000 node system and realizing that actually it's all very well and good that you've got this 300 flop socket, but because of your communication patterns and I/O, you're actually using, you know, you do even LIMPAC, which is local and embarrassingly parallel. Look at the average number of flops per core that you're actually getting, and then factor in the fact that GPUs cheat and actually have, you know, an obnoxious number of hardware threads per core. And you really end up looking at around, again, Fujitsu is the best here, but it's like around 10, I think. Per core, 10 flops per core, when the native core on like a KNL gets like 30 or more, right? And so, you know, never underestimate communication as an important part of the balance equation. And for data-centric applications, storage is equally important. So balance isn't just about compute and memory. It's compute, memory, storage, I/O, and then facilities guys would throw in air conditioning, I suppose. But
All right, so we had one last question down here. Simon, front row. Where's the mic?
So I think this is the year where ARM-based products are seriously entering HPC for the first time. So it's really exciting. Can I ask each of the panel members what you think are the biggest barriers to ARM going on to being successful in HPC?
Barrier. Should I start? Maturity of the ecosystem. I think that's the key thing, right? Otherwise, we have these big, hot paperweights. I think execution. I think we're competing against a lot of legacy code, and we are not a $60 billion company that can afford $1 billion worth of software research per entity. So I think execution across the community, efficient execution is going to play a big role in this.
I think maturity of the software ecosystem and demonstrating that we can, deliver a system that delivers good, absolute performance for real problems is going to be very important.
Yes, same answer to them. So it's very important. Currently, the HPC ecosystem is built on the IA platform. So in the ARM platform, it is very important to migrate the IA architecture application to the ARM architecture. It's very portability. It's very like someone not only recompilation, that kind of software package level. So I talk about some workshop. So it's very important to the ecosystem. So ARM and maybe that's really OS binary level, binary compatibility to build the ARM architecture. That is very important. So different microcode, however, ISA is same. On top of the system software, the same application run on the IA architecture, that also run on the ARM architecture. That's the another thing is in the ARM architecture, just a single binary can run every ARM platform. That's a key issue, and maybe another thing, point is SVE. That is not defined exactly vector length. That is a migration. For in that case, Intel case, every architecture, there are not compatibility of the generation. However, ARM is a SVE that provides a future generation with 10, 24 bits. In that case, maybe each migration is even if a different vector length provided. That's a key issue to successful ARM architecture.
In the same maturities ecosystem, especially for ARM SVE and compiler. So to be honest, without SVE, the ARM cannot beat the Intel.
Yeah, I'd agree with everything that's been said so far. I mean, I think maturity is important. I think standardization is very key. I think a lot of people want to just get a machine, have the same experience they've always had, turn it on, looks very similar to what you know and love, or maybe you don't love it, but you're trying something else, and you want it to behave very similarly, have the same experience, probably want to run very similar software. You're going to have to recompile some of it. I would agree that the extensions like SVE are very important to that. And again, there's standardization there. If we've had lengthy discussions over the past few years about handling migration of VMs from machines with different vector widths and making sure that that will work correctly. And so we've put a lot of work into this. We've done it. I think this year is going to be the first test to see how well that goes. But ARM is in with a fighting chance. I would just push people to continue to focus on fit and polish and out-of-box experience.
So I really believe that there's no technical reasons we can't succeed in this space, right? I think maturity is something that's rapidly developing. I think we're at a point where we've got the architecture to a point where it is viable. I think we've got microarchitectures that are coming out now that are viable and competitive in this space. So I think a lot of it's going to come down to business and business value for our partners, right? They need to be able to make money doing this and see the value of doing this in some of their other markets as well, for them to be successful in this space. And so it's incredibly important that as a community we support each other and we work on this, and that we are resilient. You know, we have a really nasty challenge in that almost all of our system integrators have an existing supplier that is not afraid to use their dominant position to punish those system integrators for thinking about doing something else. And this has been a consistent problem as we've tried to enter this market. And I think it's important for us to stick together as a community and persevere against that. And I think the end users are aware of what's going on, and they're not happy about it, and I think that works to our favor. But it is a nasty problem, and this is why monopolies are really bad things, and why diversity is incredibly important, not just in this market, but in all markets.
All right, so we have time for exactly one more question. You have an actual question, not a statement. Oh, yeah. I'm gonna hold you to that. All right. Oh, rejected.
So to pile on John's and Eric's answer, do you think, so a few connects ago, Linus Torvalds went there and he said, I'm mad at ARM because I never had the opportunity to have an ARM laptop. And that is why he never cared about ARM Linux or whatever. Now, do you think that, because this has nothing to do with the HPC, but it actually has. Because you see everyone asking, what about the instruction set? What about, how do I do this? How do I do that? How do I build stuff? So for the big vendors, that probably doesn't matter. But for the ones that actually also do small stuff, that could actually be a way to leverage the architecture into HPC by actually making developers use laptop. I would love to have an ARM laptop, an actual ARM laptop.
You want to take that?
Yeah, so I'm still not sure if it was a question. I don't disagree with you. I don't disagree with you. And in fact, you know, this was a common thing for power when I worked at IBM as well, right? And I think it's incredibly important. And it's not just for the lone open source developers either, right? A big challenge in relation to my previous response for our customers being able to make money in this space is ISVs, right? Who are not open source and who people can't just go and recompile their codes because they're binaries. And that is a huge problem here because they're in the middle market of high performance computing, which is where all the volume is. That's ISV dominated. And we're in it, where we have a chicken and egg problem at the moment where those people are saying, well, show us the customer so that we should do all this work for, and the customers are saying, well, we're not even going to think about you unless you support this ISV, right? And so we've been working to short circuit that by connecting those people so that they hear from each other. But again, viable development platforms and cloud developer instances and things like that, where these ISVs can go and feel confident that they can develop their code there and have it be still secure and so forth, is a very important part of that aspect of this, and it deviates a lot from leadership HPC, but it's incredibly important in this mid-market high-performance computing world.
But you can't deviate from the whole HPC, so it could be like a wild goose chase. Do you see what I mean? That's my question. Do you think this is...
So are you trying to make it into a question versus... Okay.
Well, let me throw something out there then. I want to throw two comments out there. Well, firstly, one observation. There's a keynote starting very shortly. And I'm just rooting. Come on, you can do it, guys. Come on, bring me that ARM laptop. I know you've got it in you. Just do it today, right? Every time I say it, and every time I'm disappointed, but one day they'll do it. Seriously though, I think the problem we have today is we have everyone out there in this audience who has a laptop in front of them reading their email has a processor in there with a core designed by a large incumbent, and the same microarchitecture there is then tuned, but it's a very similar one that goes into their server class parts. In the ARM case, that's not going to be the same. So, every time someone says to me, "Oh, I can get you a souped-up Raspberry Pi and a laptop," I know you're going to respond differently to that, but it needs to be a server class processor core with server class semantics and behavior to be interesting and useful, rather than just a wimpy laptop, souped-up mobile part. So that's the big problem we have. I don't think it's going to move the needle for HPC or for server in general to have those laptops and workstations for that reason. I would love to get one, but I actually don't think we're going to get the kind of processors that I would want to have, just looking at one person in particular at the end there, as an example, in the server space. I'd love to have one of his in a laptop. I'm not going to get it.
But it may be viable to have workstations.
Yeah.
So, and there's nothing wrong with that, right? Yeah. And there you don't have the battery power constraint optimization problem, right? And so we are starting to see some of those in the CAD space. The Thunder X1s have a workstation version, and there's I hear there's others coming based on some of the other server class parts, and hopefully.
That'd be nice.
Everything,
yeah.
right?
Yeah,
and those would be a good, especially for those ISV communities, to be able to develop software on those. Yeah. I think that's not having something on. At the end of the day, some developers just like having a machine there that they can touch, and that's awesome. And for OS people, it's important because we screw up and we have to hit the reset button. But I do think there's a path there.
Awesome. Okay, we have actually, that took a lot less time than I thought it was. We have time for one more question from the audience. So anybody want to raise your hand? One last one. Just one more. One more question. All right. That's right. Oh, no.
Do you have a question?
No.
Oh.
Okay. In that case, let's go ahead and kick off the closing remarks.
Okay. Can you get the slides up?
I can. Quickly.
Are we putting up the Apple keynote? Is that
Apple keynote. So first of all, let's do a round of applause for all of our panelists being brave up here. And now, so we've got sort of the organizational announcement. So first of all, thank you very much for being here. There are two things, four things. So one, the pre-dinner drinks and the kind of poster and demo session are happening in the CWB building, kind of like last night. So the one kind of at the other end. And I think they're starting in roughly 15, 20 minutes, give or take. And then the dinner will be followed in the dining hall and the garden restaurant. So please do stay for that. You can grill them more afterwards. We also have an ARM HPC users group, where basically you can go and share your experiences of using ARM, and you can also get lots of guidance from other people in the same situation. There are HPC, for example, tutorials there on how to use codes and such. That's the top QR code. The bottom QR code is kind of goingarm.com. It's the website where you'll find all the slides. Not yet. We'll stay in the process of uploading the slides and still retrieving the slides for today. But in a week and a half max, you should have all of the slides for goingarm.com up there, available for everybody. And future events, there will be an ARM HPC users group at SC17 on the Monday. And if you've got more questions about that, we've got Darren in the audience, and Darren can answer more about that. Okay? Thank you very much again, and enjoy the drinks. Yep.
me, baby. I'm calling. Come catch me, babe. I'm falling. Come save me, babe.